and device fabrication. Dr. Girison has published over 220 peer-reviewed research papers, 3 book chapters, and has successfully completed 11 major funded research projects supported by national agencies such as CSIR, UGC, DST-SERB, RUSA, and others. He has supervised more than 80 postgraduate students and guided doctoral and MPhil researchers contributing to the academic growth of future scientists. His impactful research is reflected in his H-index high citation record and recognition in international scientific databases such as Scopus, ORCID, Publons, Google Scholar, and IRINS. Notably, he has been ranked among top 2% scientists in the world by Stanford University and Elsevier in the year 2024. A recipient of 29 awards and honors, Dr. Girison has been recognized for his outstanding research contribution, best paper presentation, and excellence in teaching. He has delivered over 100 invite talks worldwide, presented at international and national conferences, and served as a reviewer for more than 60 high-impact journals, including ACS, RSC, Elsevier, and Springer publications. In addition to research and teaching, he plays active role in academic administration as coordinator for PhD qualifying examination, chief superintendent for university exam, and board of studies member in multiple institutions. He has also engaged in editorial responsibilities, serving as a reviewer editor for Frontiers in Chemistry, Nanoscience, and continues to contribute to academic bodies like UGC CAR Journal Committee. Through his commitments to innovative research, academic excellence, and leadership, Dr. Sabari Girison continues to advance the frontiers of nanophotonics, laser photonics, and sustainable energy technologies, making significant contribution to science and society. We are happy to invite him to the faculty development program. Thank you.
Thank you, Kavita ma'am, for the wonderful introduction. Now, with great pleasure, I invite our esteemed resource person, Dr. T.C. Sabari Girison, to kindly take over this session and share his insights with us. Sir, please.
Am I audible?
Yes, sir.
Okay, thank you. Hope the screen is also visible.
Yeah.
Okay. Right. So first of all, thanks to the management of Marthandam College of Engineering and Technology, Kanyakumari, for inviting me to share our research expertise, right, through this 6-day international faculty development program. Special word of thanks to Anisha ma'am, right, for inviting me to be a part of this program. Fortunately, right, this is my second talk today. Right, I was requested for a presentation for this faculty development program. Unfortunately, the organizers had made me a slot on the same day. Right, so hope I'm audible with my voice. Right, if you have any inconvenience, please let me know. And with the time allotted, since this is going to be a faculty development program and there may be people from different disciplines, I just thought that I could give some presentation, right, covering both basics, right, and advanced concept of certain fields, along with some of the research results that we have obtained. If you are familiar to laser applications, this particular part will be right, useful for you at your last half. And if you are a beginner to this particular field, I believe the next 1 hour and 15 minutes will give you some ideology, right, how to approach these type of fields. Right. So with this particular opening note, I will just go to my presentation. So, okay. So this is going to be my plan of talk. As I have told you, right, I will be talking more on lasers. Since this is about smart materials, let's talk on material aspects. So as I have told you, I am interested to talk about some of the very interesting materials and their laser applications, right? So I have divided my presentation into two zones. In the first zone, I will be talking about lasers, nonlinear optics, right, and in specific optical limiters. In the second half, I will just give you some glimpse of the importance of nanoscale, and I will talk about graphene, some of the very interesting laser experiment, and the applications that we can derive from that, right? And it all starts with some of the Nobel Prizes in physics and chemistry, which has a little bit connection to your title, right? Smart materials, energy and things, right? Technologies. So I just take 1 year back to the Nobel Prizes, right? As you all know, that Nobel Prize for Physics in 2024 was given to computational physics. Both physics and chemistry has their background from computational physics. I just take you 1 year back, right? The Nobel Prize in Physics 2023 was awarded to three great scientists, Annie Huller from Sweden, Krauss from Germany, and Agostini from US, right? They were given the Nobel Prize for their experimental methods that generate attosecond pulses of light for the study of electron dynamics in matter, right? Of course, Annie Huller was the pioneer, right, who gave the idea of subatomic physics scale based attosecond light generation possibility. Then later, Agostini and Krauss developed two independent techniques to generate attosecond light pulses, right? As the title head says, this is all about the experimental demonstration of the generation of attosecond pulses, right? So I have to start out with what is so special about attosecond pulses. And it was mentioned that it gives us the provision of studying the electron dynamics in matter, right? So I will just hint you why it is going to be special in terms of electron dynamics. So when someone asks what is attosecond, right, you can put it on a simple time scale. The age of the universe was believed to be 10 power 18 seconds. So hope you will understand how magnified that particular time scale is. If you put the reciprocal of this particular number, right, you will get to a very confined, very small, precise time scale, right, which comes at the order of 10 power minus 18 seconds, right? So generating a light pulse, right, whose width is going to be in the order of 10 power minus 18 seconds, has grabbed the Nobel Prize for Physics in 2023. Right? The reason being, when this particular light pulse was generated, right, people rejoiced for one reason, that this particular light pulse is going to have a time scale matching the time scale of the electron dynamics, right? We all know that the electrons inside an atoms or molecules or in condensed matter physics, in a condensed matter, right, they move at the scale of 10 power minus 18 seconds. So attosecond light pulses are going to be special for a reason, that these pulses will have now a time scale in par with the time scale of electrons. So this will give us the possibility to visualize and record what is happening at the electron world, right? And that's the reason why the Nobel Prize was given for the experimental techniques that has generated attosecond light pulses, which gives us the provision of expanding the electron dynamics in matter, right? So I have to be very keen on saying you why these attosecond light pulses is being discussed at the forum of discussion on lasers, right? I will just put forth a point. You all know that lasers are going to be one light source which emit light as a continuous wave. These particular continuous wave can be converted into a pulse, right? By putting a simple concept of obstacle or shutter in front of it. Imagine I have a light source, a light is coming out of it, I put an obstacle, all right? The photons that are coming out of it, right, will not be allowed to pass through this particular obstacle, which I'm going to call it a shutter. So the photons accumulate here. If I open the shutter and close it sharply, when I open the shutter, all the accumulated photons will try to come out, right? And once I close it, again the accumulation takes place. And when I open, the accumulated photons comes out. And when I close, right, the photon coming out will be stopped. If you draw the Gaussian for this particular process, you will see that the light intensity will be at 0 until the shutter is open. Once the shutter is open, a huge number of photons will be coming out of that particular system, making the profile to reach its maxima. Then when the shutter closes, the amount of photons coming out will be falling out and it will reach out 0. So you will have a Gaussian profile. You call these as a light pulse. Light pulses are generated generally to increase the intensity of the light, right? Because with continuous wave, if you can reach out to some scale, these pulses will give us the provision of increasing this particular light scale. And here, the width of this particular pulse is called as the pulse width, right? About which we are talking about, right? When this pulse width is going to be in the order of 10 power minus 18 seconds, right? You call that particular light pulse to be attoseconds, right? And what is interesting with this light pulse is that, imagine if I have a nanosecond pulse, right, whose width is going to be in the order of 10 power minus 9 seconds, right? If I say the pulse is of certain height, when I reduce this particular width from 10 power minus 9 seconds to 10 power minus 12 seconds, which you call it as picosecond light pulse. When you shrink them, the height of this particular pulse increases, which I'm going to call it as, right, the increase in peak intensity, right? So whenever the pulse width decreases, right, the peak intensity increases, which means that you are getting a light of tremendously, right, large intensity, right? And when this time scale was brought to the order of 10 power minus 15 seconds, which we call it as femtosecond light pulses or femtosecond lasers, right? People rejoiced this particular discovery, and the invention of these femtosecond light pulse generation was given the Nobel Prize in the year 2018. The reason being, when femtosecond light pulses were generated, right, the chemist rejoiced with these particular light pulse because all the molecular and atomic chemical reactions takes place at the scale of 10 power minus 15 seconds, right? And this makes a sense. Now I have a light pulse, which will have the capability of recording how do these particular atoms convert themselves into molecules, and you can study the atomic and molecular dynamics, right? Imagine if I have a water molecule, you all know that oxygen molecule will be binding with, make a covalent bond with 2 hydrogen atoms to form H2O, right? So we have animated this particular process, but we have not visualized what is happening here at this particular scale. With this femtosecond scale, it is now possible for us to see what is actually happening at that particular scale, because this reaction takes place at the order of 10 power minus 15 seconds. And that's the reason why if you go for chemistry now, you have a separate branch called as femtochemistry, right? So these femtosecond light pulses, when it was invented, people made a statement that sooner or other, there will be one more Nobel Prize on this particular division, right, for 10 power minus 18 second attosecond, because when you go to 10 power minus 18 seconds, right, you just penetrate into the atoms and you go to the time scale of electrons. Any electron that transit from one energy level to another energy level, or the electrons that move around the nucleus, right, have the time scale at the order of 10 power minus 18 seconds. So with this particular light pulse, you can see how do your electrons actually behave within your atoms and molecules. Not only this, when you string this particular scale to 10 power minus 18 seconds, the peak intensity increases enormously. So attosecond light pulses are going to be rejoiced for the second reason that this is now the highest, right? This is going to be the light that has the highest intensity as far as our Earth is concerned. right? So such high intensity light has a lot of technological applications. We will talk about those particular stuffs later, right? And this is the reason why 10 power minus 18 seconds is rejoiced, right? And that's the reason why Nobel Prize was invented, right? Given to these particular experimental techniques that generate these attoseconds. As you can see here, if I move from a stopwatch, which moves at the scale of 1 second, you move to the millisecond, you will be reaching out the camera shutter movement speed, right? And if you move still further, right, you can go to the chemical reactions at the scale of 10 power minus 6 seconds. And when you go to nanoseconds, you can look for these particular optical switches, right? And when you go to 10 power minus 12, you could visualize molecular vibrations. And as I have told you, when you get into the femtosecond, you could see the real atomic and molecular reactions, right? Say, for example, if photosynthesis takes place, right, the generation of glucose can be visualized with these particular light pulse, right? And when you go beyond 10 power minus 15 seconds to 10 power minus 18 seconds, it is going to be interesting. You are getting into the atoms and you are going to visualize the movement of your electrons within atoms and molecules. And that's the reason why the Nobel Prize was awarded with the statement that it explores the electron dynamics in matter. Right? And as I have mentioned, we will take this particular platform to make a note that sooner or later, we are going to get one more Nobel Prize on this particular division, right, for the invention of generation of femtosecond light pulses, whose scale will be in the order of 10 power minus 21 seconds, right? And when you get into that particular scale, still you can go penetrated into your atom, you can get into the nucleus, right? And you can see how do the nuclear reactions take place. Nuclear fission, fusion, all these particular dynamics can be visualized when femtosecond light pulses are going to be realistically possible. As of now, researchers are going on all over the world, but still then, right, the generation of attosecond pulses, right, is at present revolutionizing the entire technological world. Right. So when I was doing my research, right, my PhD way back by 2010, when I was approaching foreign universities for PDF, they used to ask me whether I have experience of handling femtosecond lasers. All right. Interestingly, at that particular time, India has 2 or 3 laboratories because of the cost of these particular laser. But after 2018 Nobel Prize awards, right, the cost of this femtosecond has considerably lowered, but still it is costlier. And more than hundreds and hundreds of institutions are having this particular femtosecond lasers in India, and intense research is going on. Likewise, attosecond pulse lasers are going to be realistically soon possible, which is going to give us the provision of exploring many exciting, right, domains of higher harmonic generations, electronic transitions, multiphoton tunneling, right, electron localization, double ionization, all these particular phenomena are going to be explored very shortly with these attosecond lasers. So with this particular note, right, I will just get into the core point of why I have to look upon lasers. As I have told you, lasers is going to be a very interesting tool, right, in technological world, because it is giving lot of solutions and it is making revolutions with the technology that is present at present. After the invention of laser in the year 1960s, whose pioneer is going to be Macet, which was invented in the year 1950. The first Nobel Prize for this particular field was given for the invention of Macet in 1964. Soon after, you just see, right, in a period of very short period of 60 years, Nobel Prizes related to lasers is increasing predominantly, right? And as I have told you, right, laser spectroscopy, right, got the Nobel Prize in 1981. Laser cooling of atoms, which has given the possibility of experimental demonstration of Bose-Einstein condensate and nuclear fusion reactors, got Nobel Prize in the year 1997. Later in 2000, right, semiconductor lasers was given the Nobel Prize. Soon later, mode locking lasers, which has the capability of generating pulses at the scale of 10 power minus 9 seconds and 10 power minus 12 seconds, got Nobel Prize in 2005. It was a bit an old story because in 2018, the ultra-short pulse laser generation, which falls at the scale of 10 power minus 15 seconds, was given the Nobel Prize. In between, the mind-blowing fiber optic communication got its Nobel Prize in the year 2019. Still, 2018 is not the last lap. The science has advanced too much. In 2023, we entered into the domain of attosecond light pulses, right? And this list is not going to end here. It is going to increase in the upcoming years also. And that's the reason why, right, I have chosen the technology for today's discussion to be lasers, right? So let me go quickly into some of the basics of lasers, right? As I have told you, since I'm afraid there may be a mixed audience, I have covered it from basics towards advanced and research level, right? So to start out with laser, I often tell people that all the light sources that are around us are not the same, right? So I have just listed some of the light sources around us, right? The sun, incandescent bulb, candle, right? Jellyfishes, radium watches, right? Likewise, there are many light sources among them. If you look at the phenomenon that is responsible for the emission of light from these particular light sources, they differ. If you go for sun, it is going to be nuclear fusion. And if you go for a bulb, it is going to be electrical discharge. If you go for a candle, it is going to be combustion. Right? If you go for a jellyfish, it is going to be bioluminescence, right? Likewise, right? All light sources have their own phenomenon of light emission. But one common point among all these particular phenomenon is that the light is emitted from this light source using an optical phenomenon called as spontaneous emission. As you all know that, right? The electrons in the ground state absorb photons and they move themselves to the excited state. And in the excited state, they cannot remain for a longer time. So they emit the same photon out and they get back to the ground state. This process is called the spontaneous emission. All these light sources emit light through the process called as spontaneous emission, right? The only light source that works on the phenomenon called as stimulated emission is going to be called as laser, right? As the word implies, laser is all about light amplification by stimulated emission of radiation, right? And stimulated emission is going to be a very special case in which the excited electrons, before they get back to the ground state, they will be bombarded with another photons and they will be forced to come down. And what is interesting on this particular process is that the photons that are coming out of stimulated emission are going to be in phase, which gives the characteristics called as coherence. And as this particular electron transition is going to take place between a precise energy levels, the wavelength is going to be single. That makes this light monochromatic. And since this particular light travels in monochromatic phase, right, with coherence, right, they have the unidirectionality character, which means that they have a very little beam divergence. And since these photons are jam-packed through the process of coherence, they always have high intensity than conventional light. All these particular things makes these particular lasers special and different from all the light sources that are available around us. Right? Just to have a quick look on the history of lasers. Interestingly, the journey of lasers started with Albert Einstein in the year 1916, who just formulated for the first time, right, the concept of stimulated emission using his theoretical equations. Right? It took 12 years for the scientists to prove experimentally the existence of stimulated emission in laboratory. Rudolf Ladenburg did that particular one. And soon after that, right, people started working on developing light sources using the stimulated emission process, right? And as you all know that for a stimulated emission to occur, you should have more number of electrons at the top, right? So you need a condition called as population inversion. And the possibility of population inversion was experimentally demonstrated by Arthur Shavlow in the year 1930. And from 30, right, people started working on developing a light source that works on stimulated emission. By 1950, two research groups accidentally, right, invented these particular light source together parallelly, right, one from Russia and other one from US. They named that particular light source as microwave amplification by stimulated emission of radiation, right? And later, this microwave was extended to the other electromagnetic spectrum, right, to the visible light domain, right? And the first visible light laser was demonstrated in the year 1960 by Theodor Maiman, the ruby laser. And on the same year, at the end of that year, Ali Jawan, right, invented the first gas laser, helium neon laser, right? So this is the reason why the Nobel Prize was given to the invention of maser, not laser, right? Because the maser was going to be the prototype, right, that has given a light source using stimulated emission, right? Later, after 1960s, plenty of light sources, right, on lasers were invented, right, and still these particular lists keep on going, right? As the word L stands for, it is going to be light, which means that it is an electromagnetic spectrum. At present, we have a very strong, right, list of laser sources from infrared to visible to ultraviolet. Of course, radar, radio waves, and electric waves are longer wavelength light sources, so they have no practical importance, right? At present, we don't have lasers at the spectrum of X-rays and gamma rays. This is because in laser, you have a layout, right, in which the stimulated emission photons are allowed to travel to and fro between two mirrors for amplification, right? So you need two mirrors, one with 100% reflecting, another one with 95% reflecting to do the process of amplification, right? We at present, we don't have any mirrors which has the capacity of reflecting X-rays or gamma rays. When such mirrors are going to be possible, right, you are going to see that X-rays and gamma ray lasers are going to be directly possible. But at present, we have a considerable number of lasers from infrared to ultraviolet domain, right? So this is again, right, the field is expanding too fast, right? When you go for a search on this word laser, you will come across the terms like white lasers. The actual word comes as white supercontinuum lasers. When I started the definition of laser, I have mentioned that laser is monochromatic. But you all know that white lasers are polychromatic, right? Which means that they have different wavelengths. And we all know that by physics, light of different wavelengths cannot travel in phase, which means that they cannot be coherent. But still, we have white lasers in market, right? Along with the word supercontinuum, right? So white lasers are generated, right, with the concept that you imagine if I have a red laser, its wavelength is going to be longer. Imagine it starts somewhere else here. It travels, it reaches some point. All right. And if I keep this distance as the same, and if I ask a green light to travel, they may make more number of waves. Imagine they also ends up at the same point after some distance. Right. Likewise, if I bring a blue laser, they create more number of waves and they end up at the same point. Now, if I repeat this particular distance, right, periodically, you could see the start point and end point are going to be the same. You call these as supercontinuum coherence, right? And with this particular provision, it is possible for us to bring lights of different wavelength in coherence. This is how a white laser, right, is generated, right? In practicality, right, these lasers are generated by coupling, right, three primary colors, red, blue, and green, through optical fiber. What you see here is the experiment that has been performed in RRCAT indoor, right, wherein red, blue, and green lasers are coming through optical fibers. They couple them together, and when they come out as a white laser. So what you see here is the light that is going in, and the output is going to be white, right? And this white is going to be called as a laser because they are going to have coherence with supercontinuum structure, right? So these particular invention of white lasers is already revolutionizing the entire optical world, because when these optical white lasers are going to replace the conventional light sources, it is going to create a lot of, right, superiorities than the things that we have, right, all around us, right? And again, the science of this particular concept is still an older one, right? Technologically, white lasers has been converted as a headlight in BMW i8 series. Now we are at BMW i10 series for long range visibility, right? So white lasers, right, are the present talk of the laser world, right? Because they are going to be advantageous, right, in terms of photography, in terms of recording, in terms of illumination, in terms of visualization, and the list goes, right? So with these fundamentals, right, I will just go quickly into the application of lasers, right? When the first laser was demonstrated, ruby laser was demonstrated, the inventor Theodor Maiman in 1916, he made a statement in a press conference that Laser is a solution looking for a problem, right? And this particular statement holds good even after 65 years. Whenever we approach the laser with the scientific problem, it always has given us solutions. And that's the reason why lasers are everywhere and it is almost inevitable, right? I have just given you some of the glimpse of laser applications. You all know that the entire communication now relies on fiber optic communications, right, which requires lasers. And the photography technology is no longer going to be two-dimensional. It is going to be taken to three-dimension, and you call these processes hologram, which requires laser. And when you go for optical data storage, right, initially we used to floppy disk. Later we have converted them into CDs, then into DVDs. Now we have Blu-ray disc. The basic difference between these things is that from your CD to DVD, we use red lasers to read and write. And when this red laser was replaced by blue lasers, right, you call it as Blu-ray disc. And what is interesting is when the laser wavelength decreases, the spot size also decreases. So which means that with blue light, I can read and write more number of data. And that's the reason why Blu-ray disc can hold more data than your DVD. Right? So lasers are used in these particular technologies. Right? Apart from that, when you go for the world of material processing, laser welding, laser cutting, laser drilling, and laser-based technologies has already been evolved and they are used right in automobile industries and all right material processing based sectors. And when you go to medicine, right, these lasers are going to be called as the weapon that can create bloodless surgeries. Cataract operation, which was believed to be a major surgery once upon a time, now with the term called as LASIK, it is going to be an RF operation. Put a hole, right, send the laser through that particular system, right, pass the lens, right, make them replaced, right. All these particular things can be done without any, right, blood loss. And lasers are already becoming a very strong tool in biomedical sectors, right. Not only the constructive applications, these lasers are also used, right, as a destructive weapons. Imagine a spy satellite is coming above our country. If I shot them with missile, even though it is a spy satellite, it is an international problem. Imagine I give you an infrared laser. You all know that infrared light are not visible to human eyes. If I can focus this infrared laser upon this spy satellite, it will create a localized heat which can make that particular spy satellite to burst. You call these particular weapon as directed energy weapon. This is not a science fiction, right? All the developed nations and developing nations have a separate sector called as DEW in their army, right? Including India, we have DEW, right, which has the capacity of, right, hitting any of those particular things that are coming towards us by focusing an infrared light upon that particular system. You can break down the system without any signature. And that's the reason why directed energy weapons are believed to be the next generation weapons, right, which is going to give a lot of shielding for a country, right? I'm pointing out all these applications for one simple reason that these lasers, right, are technologically important and they are already replacing all the conventional light sources that are available in technological world. Not only technological point, these lasers are special. If you go for a science, this laser has created an, right, a very interesting, right, changeover, changing the concept of optics from linear optics to non-linear optics, right? And we call these particular journey as journey of excitement because all those optical phenomena that are known to us using the conventional light sources that works on spontaneous emission has become an old story. And after the invention of lasers, we started coming across a lot of new optical phenomena which we have not observed before. So the journey of moving from the known light phenomena to unknown light phenomena, right, happened because of the invention of lasers. So what you see here is some of the pictures that represents the different optical phenomena. When I say moon, the reflection comes to the mind. When I say mirage, refraction comes, dispersion, polarization, dispersion, rainbow, right? And when you go for At the sunset, you talk about scattering, and when you go for butterfly, we talk about dispersion and interference. All these are conventional optical phenomena known to us. If you now go for modern day optics, right, you will be seeing some new terminologies like harmonic generators, self-focusing, optical limiters. These optical phenomena are new to this particular world, and these phenomena arises because of the interaction of laser with materials, right? And we call these particular branches era of non-linearity, right? And just to make you to understand what is the difference between linearity and non-linearity, I have given you some examples here. So what you see at the left side is the periodical marching of soldiers. I call this process to be a linear process. Definitely it looks beautiful, right? And that's the reason why we always say linearity, right, gives beauty. And imagine if you have a chance to look upon a lightning, right? The lightning is going to be, right, a process of, right, a very interesting thing to be observed, because these lightning don't have any proper shapes. Rather, they create non-linear branches, right? The beauty of these particular lightning is because of the non-linear branches they create upon the sky, right? And this particular non-linearity takes us to add a word to the word wow, right? And this beauty is called as excitement. And that's the reason why we often say non-linearity gives excitement, right? So this is the basic difference between linearity and non-linearity. And just to put it still in a simpler manner, if you travel by a giant wheel, I call that particular process to be, right, a linear process. And if you put yourself in a roller coaster, right, that particular process, I call it to be the process of non-linearity, which gives excitement, because you cannot expect what is going to happen next. So expecting the unexpected thing to happen is going to be the most beautiful part of, right, roller coaster, which cannot be observed with your giant wheels, right? Speaking in terms of physics, if I talk about a simple pendulum, I talk about harmonic oscillators, right? It is linear, and the pattern they form is going to be a linear pattern. And if you go for a double pendulum, it is going to be an unharmonic oscillator, and the pattern they are going to create is not going to be linear, right? So this is the basic difference between linearity and non-linearity. And what happens as a result is that after the invention of lasers in the year 1960s, right, the optics was divided into two groups. One is called as linear optics, and other one is called as non-linear optics. The linear optics is called as the branch of physics that deals with the study of interaction of weak electromagnetic field with matter, right? I call it as a weak electromagnetic field because before the invention of laser, all the light sources carries a very weak electromagnetic field. And the phenomenon that is coming out of these particular interaction can be explained by a simple harmonic oscillator. And the different phenomena known to us as are absorption, reflection, refraction, polarization, scattering, etc. After the invention of laser, this light source has become a strong electromagnetic field. And when this strong electromagnetic field interacts with matter, right, this interaction is not going to be linear. You call that one as a nonlinear optics. To explain this interaction, you need an unharmonic oscillator, which has given the entity of nonlinearity to all the phenomena known to us. We got nonlinear absorption, nonlinear refraction, nonlinear polarization, etc. Right? So after the invention of lasers, the nonlinear optics begins. Right? So now let me take the next couple of minutes to say you, right? When someone comes and say you, when lasers interact with matter, the system turns nonlinear, right? So the basic question that will come to our mind is that why does it originates? Where does this nonlinear optics originates when laser interacts with matter? Just you have a look at these particular two pictures. What you see in the left-hand side is a line chasing a zebra. Of course, line is stronger than your zebra, and so line is dominant than zebra. But what you see in that right-hand side is an elephant chasing a lion, because elephant is stronger than my lion. Now, if I ask you whether my lion is a brave or coward, right, it's going to be an interesting question because the situation decides that. Compared to zebra, my lion is stronger. Whereas compared to an elephant, right, my lion is weaker. This is the scenario that has happened in, right, the interaction of light with matter, right? When conventional light interacts with atoms, right? You all know that atom carries a electric field within them, and your light is going to be an electromagnetic spectrum. So they carry an electric field. So when these two comes together, they interact with each other. So the interaction that happens between them is just like a interaction between a lion and a zebra. Here your line is going to be your atom and your zebra is going to be your conventional light. But when the laser comes, it is something like putting an elephant in front of a right lion. So what happened is that the laser started dominating, right, the light. Started dominating the atoms. The reason can be given by simple numbers. The electric field that prevails within your atom is in the order of 10 power 7 volt per centimeter. But when you go for a conventional light, right, the scale of electric field that is available with the normal light is in the order of 10 power 3 volt per centimeter. So when these two electric field interacts, it's quite natural. Atom dominates the light. But when you go for lasers, the electric field of the lasers comes at the order of 10 power 10 volt per centimeter. So when these two interacts, for the first time, the laser started dominating the atoms, the molecules. So what happens as a result is, you got a switchover in the scenario, right, moving from materials controlling light to light controlling the materials, right? I call these particular processes master-slave flip-flop because the master atom in the first case has become the slave in the second case. What happens as a result is, when these particular lasers started controlling these atoms, they started manipulating their property by themselves. And that's the place where the nonlinearity originates and different nonlinear optical phenomena arises. Just for you to understand quickly, if a red light is allowed to pass on a material that absorbs light, it will absorb all the photons and they will emit them out, right? So this is a linear process. Imagine if I send a red laser upon the same material, they will be absorbed. But what is interesting is, since this process is going to be non-linear, you can expect something unexpected to happen. And what happened is, along with the red light, there is an emission of new light at the scale of blue or below, right? And people started asking, where does this blue light comes from? Because I have passed a red light, but a blue light is coming out, right? And people called these particular process as a nonlinear process. And that particular branch is called as nonlinear optics. And these arises because the laser started controlling the materials. As a result, they started changing their characteristics by themselves, right? And this is the reason where the different optical phenomenon actually originates. I have given you some of the beautiful examples of the optical phenomenon, right? Let me start with polarization. You all know that polarization is going to be the process in which the multiple vibrations of a light is synced to one particular vibration, right? That's what a polarizer does, right? And that's the reason why a polarizer avoids glare in car windows, right? So when a yellow light passes through a polarizer, all the lights will be cut off and you will be getting only one particular light, and which will be yellow in color. This is called as polarization, linear polarization. Imagine I put the same polarizer and I send a laser into that particular system. The polarizer do the process of converting your multiple reflection into single reflection. So if I send a red light, I expect the red light to come out. Along with the red light, imagine if blue light is coming out of that particular light, right? That particular polarizer. You cannot call that particular process to be a linear polarization, right? I call that particular process to be a non-linear polarization. I put it for your better understanding. Imagine I am coming by car, I emit a red light through the laser. You are coming towards me through a car in which your car is having a Polaroid to avoid glare, right? When you sit inside the car and see, right, if this process is going to be a laser coming in, right, instead of red light, right, I will be coming across seeing some new color of light coming, blue. If I come out of the car and see, I see red light coming. But if I sit inside the car, I can see a blue light coming, right? So the process of wavelength change cannot be explained by a linear process, because polarization has to cut off the wavelengths, has to cut off the vibrations, not to change the wavelength. But these wavelength changes occur, right? To understand this particular concept, let me take you to nonlinear absorption. In absorption, what happens? An electron absorbs a light, it moves to the excited state, and then it falls off. Right? So one photon is absorbed and one photon is excited. Imagine an electron absorbs a light, right? It moves to excited state. Before they fall off, they absorb another photon and they move to the excited state, second excited state. And from the second excited state, if they fall down to the ground state directly, now what happens? Two photons are absorbed and one photon is emitted. If I say the frequency of one photon is omega, right? Now the light that is emitted will have the frequency 2 omega, right? So when the frequency is double, the wavelength will be reduced by half. So when I send a red light, I could expect the light to be emitted with wavelength lambda by 2. Lambda by 2, right? And that particular wavelength change is going to be called as harmonic generation. And this phenomenon is called as two-photon absorption, right? In conventional world, we can experience only one photon absorption. But when you go for non-linear absorption, you could expect multi-photon absorption to take place, which gives us the provision of manipulating the optics. Optical modulations can take place, right? And similarly, you can extend these particular concepts to the concept of refraction, right? You all know that when a laser light passes through a medium, when a laser passes through a medium, it creates a local heating. Since this laser is going to be a Gaussian profile, the heating will take place maximum at the center, right? And the heating will be reduced towards its state, which means that when a laser passes through a medium, at one particular point, the temperature will be maxima, and at some point, the temperature will be minima. So when this temperature changes inhomogeneously, it changes the density of the system, because we all know that density is a function of temperature. So when the density changes, it changes the refractive index of the system. So what happens now is, when a laser passes through the medium, it converts this particular material into a material that has slabs of different refractive indexes, right? So they make the material to behave like a lens, a thermal lens. And what happens as a result is, the laser that comes through the system, right, converts this material into a lens, and this lens will either converge the light or diverge the light. So when a laser passes through the medium, they have the capacity of, right, focusing themselves within the material itself. You call these processes self-focusing process. And sometimes when a laser enters through the medium, they diverge themselves and they come as an expanded beam. You call these particular processes self-defocusing, right? This is nonlinear refraction. Likewise, there are plenty of optical phenomena that arises, right, because of these particular laser interaction with materials, right? So with these particular phenomena, let me go into the precise, right, application where we can look upon, right? To introduce that particular phenomenon, right, let me talk about the adverse side of lasers, right? I have shown you a picture in which I have shown you three light sources. One is sun, other one is lamp, maybe 100 watts lamp, and the other one is going to be a normal diode laser that we use it in our presentation, right? If I ask you, looking upon these light sources, which is risky, normally we say sun because it has a huge amount of intensity, but it resides somewhere else. So looking at the sun, right, may not harm us looking at a 1000 watts bulb, right? But if I ask you, compare looking at a 1000 watts bulb or a diode laser directly, right, a pointer laser directly, right? Normally we go to the choice of the risk for 1000 watts bulb. Imagine if I put the intensity of all these light sources to be uniform. So let me say it is 1 milliwatt per millimeter square, right? And if I see these three light sources, the power density of this light, when it falls on the retina, will be in this particular order: 0.1, 0.15, 300, which makes a sense. Looking at a diode laser is going to be 3000 times more hazardous than looking at a sunlight, right? The reason is going to be very simple. We all have played this particular experiment when we were at our schoolings. Take a convex lens, put it in front of a paper. The sunlight will be focused through a small portion. An enormous heat will be generated and it will burn the paper, right? This is the same thing that happens when you look upon a laser. Look at this particular case. When you look upon a normal bulb, the light that falls on your lens got diverged and it falls on the retina. But when you look upon a laser, you see after the lens, these particular beam get focused. So what happens as a result is that the spot size of your image will be in the order of 300 to 400 micrometers, whereas it will be just 2 micrometers. So when the spot size decreases, the power density increases enormously. All right. So looking at a laser can create a permanent damages to our eyesight. But I have already told you, I cannot avoid lasers because they have a lot of applications. But handling lasers, right, may harm my eye permanently, or it can damage the optical components very seriously. When people were looking for a solution, as I have told you, laser is a solution looking for a problem. It gave a solution for this problem also. The simple solution to this problem is, we all know that when high intensity light falls on our eye, it damages the retina. Imagine I have a smart material, right? I introduce a smart material. Whenever a high light comes, if they reduce the light, if they do the filtering process and they allow only part of the light to come out, right? This particular problem can be avoided. They will not damage the eye. But when you use a conventional filters for lasers, this process cannot be effective. Because if you want to do the filter of lasers, you have to increase the thickness of the glasses. When the glass thickness increases, the low intensity light cannot pass through, which means that your normal filters that are used in laser goggles, right, will have a thickness OD value, right? With that, they will not allow the high light to pass through. At the same time, low light also cannot pass through. And that's the reason why when we put laser goggles, you cannot see the normal light clearly, right? But when people were looking for a solution to this particular problem, right, laser, through the concept of nonlinear optics, has given rise to an optical phenomenon called as optical limiters, right? So optical limiters are going to be a smart materials, right, which will act transparent when low light comes, right? When a low light comes, they will act like a transparent glass and they will allow the light to pass through. But suddenly when you increase the intensity of light, this glass will convert themselves into, right, a opaque nature and they will not allow the light to pass through, right? So whenever a high intensity light comes, they will allow only part of the light to come through, right? So such materials are called smart materials because in linear optics, a glass is transparent, whereas a rubber is opaque. You cannot make your glass to be opaque depending upon the condition. But any material that possesses the property called as optical limiters will allow the light to pass through, being transparent. And when the intensity exceeds a particular point, they will convert themselves to opaque and they will be allowing only part of the light to pass through. So these optical limiters can be utilized to generate laser safety devices. Very intense research is going on in this particular field, right? And that is the place I will take you to the material world, right? Finding a suitable material for generating optical limiters, for generating, right, or fabricating laser safety goggles, right? So I will take you to the materials world, right? And I'm going to confine my discussion towards nanoscale, right? We often say materials are the symbol of our civilization, right? We started with Stone Age, then we moved towards Bronze Age and Iron Age, right? And now we are believed to be in Iron Age, but the era of Iron Age is coming to an end, and the era of Graphene Age now begins, all right? As you see through the ages, we call these ages an Iron Age because all the things that we see around will have at least a part of iron within them. Likewise, in near future, all the things that are going to be around us are going to be either having directly or indirectly these graphene materials, right? And that's the reason why we call the upcoming age to be the graphene age. And the word graphene has become popular because of nanoscience, right? So nanoscience by the word means it is 10 power minus 9 meter. So 1 nanometer can hold 9 number of atoms because the size of atom is going to be 10 power 10 minus 10 meters, 1 angstrom. So I can place 9 atoms together. But in reality, these atoms repel each other. So if you go for 1 nanoscale, you could look upon 3 or 4 atoms placed one after the other. right? So there is nothing other than interesting other than this particular factor. So 1 nanoscale will take you to the domain where you can see 2 or 3 atoms of one particular material, right? But this nanoscale has become so fascinating because at this particular scale, the behavior of the material was fascinatingly different from their actual characteristics. And that's the reason why we often say nanoscience is not going to be the field in which we are in the race of finding new materials. Rather, we are in the race of understanding the real characteristics of the materials that we have discovered before, right? So just to make you understand quickly why this small 10 power minus 9 has become a big deal, right? I have shown you 2 pictures. You again see 2 pictures. In the first picture, you see a group of people catching a dog. Imagine, right? I am one of the person who is in this particular group. Let me say this is that particular person, right? On the very next day, when I come out to the streets, if I face the same dog, right, I may not be that much confident to face this particular dog. The brave person who is there in the group, who is enjoying, right, facing a dog, right, do not reflect the same characteristics when he was left as an individual, right? He was afraid of dog and he was running through. Again, if we put forth the same question, whether I am a brave or coward, again, the answer is going to be situation differs, right? These behavioral changes can be summarized as group behavior and individual behavior, right? And this is the thing that has happened, right, in nanoscale. Whatever the characteristics of atoms or molecules that are known to us are the characteristics of group of atoms. And when they are brought to the nanoscale, that is, when you bring them to be almost as an individual, you can see the real characters of those particular material, which was not the same as that of, right, their real character, the characteristic that we have observed. So the bulk characters, which we call it as a group characters, was not the same as that of the individual character. So people started searching the real characteristics of atoms and molecules. And this is the place where nano world has become so fascinating, right? And to put forth a simple example, we all know that when I say gold, it should be yellow in color. If I go for a gold shop, I purchase a gold chain, right? All the signature I will look for is that, right, it has to be yellow in color. Imagine you purchase a gold chain, and if the shopkeeper gives you a blue color chain, right, we will not accept it as a gold chain because to us, gold is yellow in color. But if you go for reality, when you reduce the size of this gold from bulk, right, to nanoscale, right, 120 nanometer, 100 nanometer, 80, 40, and if you move towards 1 angstrom, the light that is emitted from that particular material actually changes. If you take a gold at the scale of 500 nanometers, they appear to be blue. And if you take this particular gold to 1 angstrom, that is almost 1 atom, interestingly, they are colorless. So this makes a sense. Gold, which was believed to be yellow, is not its individual character, it is group character. In reality, the color of the gold is ash or colorless. And that's the place where people started exploring the real characteristics of different materials and they started using them, right, for technological applications. All these particular processes begins, right, because of the word called as 10 power minus 9, right? I have just given you a scale for your comparison. The naked eye, right, can visualize mesoscale. After the invention of microscope, we went into microscale. Now we have the capacity of extending our idea to nanoscales, right? And this is the process that has revolutionized. Optical microscope has turned themselves into electron microscope. And when the electron microscope was invented, right, the real exploration of atoms and molecules actually begins, right? So this is how a hair looked like when you see through your naked eye, when you see through your microscope, and when you see through your electron microscope, right? The real image of your hair is this one, not this one, right? And after invention of electron microscope, people started exploring, right, how does this particular nanoscale, right, is making its impact in real time, right? So nanoscale, utilization of light at the nanoscale has a lot of nature-based evidences. If you go for a peacock, we all know that the feathers creates different colors. Although they were from same material, they do not have the same colors, right? This happens because of the different size of the photonic crystals that are available within the feathers of your peacock, right? Likewise, if you go for a butterfly, right, the butterfly has the capacity of sensing different gases, right? What you see here is, if I expose the forewing of my butterfly to ethanol and toluene to another wing, you can see, right, the colors changing differently, right? Which makes a sense. They have the capacity of differentiating these two, right, gases. This is the technology we are trying to impart, right, in gas sensors. And when you have a look at the magnified scale, you could see there are a lot of blocks of atoms and molecules available. Each and every block takes part, right, in sensing one particular gases, right? So we are just making an attempt to mimic these particular concepts. Likewise, if you go to a camelon, right, they changes the color according to the environment by just adjusting the distance between the nanocrystals. If you have time, you just go through YouTube, right, you will see a very interesting, right, how do these camelon changes its color. The point I want to bring out of this slide is that nature already uses light at the nanoscale, right? So I just don't want to bore you with this particular slide. I have just collected some of the most exciting pictures, right? Right. And what is interesting when you go to this nanoscale, right, with optics is that as you move down through this particular size, right, what happens is that you are not reducing the size of the atom actually. But what happens is the interaction between your nucleus and the electron actually changes. This results in the increase in the band gap of the material, right? And this is the reason why a particular insect, right, which has the same atom with the different sizes, have different band gaps, so they have the capability of emitting different lights, right? And this is the phenomenon that is, right, observed in nature, and we call this as quantum confinement. And those molecules, those particular structures were called as quantum dots, which has received, right, Nobel Prize in the year 2023. I will come to that slide after. Right? Yeah. Right. So quantum dots, right? If I want to create one particular color, right, I have to go for one material. This is an old story. By changing the size of one particular material, I can make the same material to emit different colors, right? So this is the concept of quantum dots. And for this particular synthesis procedure only, the process of getting simplified quantum dots with simple synthesis procedure, the Nobel Prize in Chemistry was awarded, right? And quantum confinement, right, was used, right? So the point that we take away from this particular slide is that, right, atom, when it has different sizes, molecule that when it has different sizes, they have the capacity of giving different light emissions. It means that their band structures can be tuned. You can utilize these things in optics because when the band structure is getting tuned, the optical properties also getting modulated, right? So one of the interesting paper that I have recent a few days back, right, which starts with the heading, the nature's first laser gun, right? And it has a picture like this. I just want to make clear to my audience that this is an AI generated one. But the point they want to say is scientists discovered, right, peacock feathers can fire, right, a laser, right? And when you go through this, I have given the link of this particular paper. When you go through this particular paper, you will see, right, using the different feathers, right, of a peacock, right, which we call it as barbels, right, of different colors. What they have did is they have taken them and they have dipped it in a particular dye, rhodamine dye. Rhodamine dye, when it is excited, they can undergo stimulated emission and they can emit green light. And when this green light was allowed to pass through these barbels of different color, they observed, right, that light travel, right, with coherence. That makes a sense. These particular fibers, right, acts like a resonators. As I have told you in the beginning, for a laser, amplification has to take place through multiple reflections, right? And the most costliest part of any laser is this optical cavity, which you call it as resonators. Naturally, these particular peacocks have an arrangement through which coherence can be achieved. So people are now working on utilizing these type of biological materials to create low quality resonators, right, and create random lasers, right. One of the interesting papers I have read out, right. So with that note, right, I will go to the final part of my particular discussion. I am almost on time, right. I will cover my further discussion in 5 or 10 minutes of time, and I will leave the remaining time for discussion, right. So the coal, which was believed to be the most inexpensive material in this Mother Earth, has become the most costliest material with the term called as graphene after the invention of electron microscope. Right. What I'm going to do is I'm going to take this graphene as my subject of interest, because graphene has a very interesting layered structure, right, and they have a very interesting nonlinear characteristics called as tunable nonlinear plasmonic character, through which these particular materials, right, can interact with the different light and they create different nonlinearity, right. So taking this as my case study, right, in our laboratory, right, we made an attempt to understand a very exciting complexity, right. I call it as nanophotonics. As we have seen, when laser interacts with medium, the interaction is not, right, a fundamental one. It is a very complex one. You call that particular complexity as nonlinear optics. Likewise, when I bring the atom to nanoscale, the behavior of the atom is not the same, right. You have a complexity because of nano. All right. When I couple these two things, when laser is allowed to interact with a nano materials, right, you get a very exciting complexities, right, and understanding this one is termed as nanophotonics, and we have performed many experiments on these particular materials, right, nanoscaled materials, right, and we made them to interact with lasers. What we did in our laboratory is a simple experiment, which we call it as an Z-scan experiment. Z-scan experiment is going to be a simple setup which focuses a laser beam, right, upon a point, right? And through this particular focused beam, I will allow that particular sample to move through. So when this sample moves through this particular focused beam, you could see, right, what you could observe here is, whenever they move at each position, they experience different light intensities. When they come to the focus, you could see, right, they have the intensity to be maxima. And when they move through that, the intensity actually changes, decreases. So for every position, these light experience different intensity falling on them. What I'm going to do is I'm going to collect the output, the transmitted light. If I draw the graph between the transmitted light and sample position, right, I will get, right, a pattern. I call that particular pattern as open aperture pattern. And this pattern may either look like a peak or like a valley, right? This peak represents, right, a phenomenon called a saturable absorption inside a material, right? And when it gives a valley-like pattern, it gives rise to a phenomenon called as reverse saturable absorption, right? And this reverse saturable absorption is going to be the phenomenon I'm looking for to develop an optical emitter. For a material to be an optical emitter, the material should have a phenomenon called as reverse saturable absorption. Likewise, I can perform the same experiment, right, using aperture in front of the detector, collecting only the central portion, which will gives me the information about the nonlinear refraction. It may give a pattern with peak followed by a valley, or a valley followed by a peak, right? And this pattern will tell you whether your nonlinear refraction is going to be self-focusing or self-defocusing. So by performing this experiment developed by Sheikh Baghe, right, we can predict what is the nonlinear optical phenomenon that is present inside this particular material. So with that case, right, I have I will just quickly go to the material discussion, right, what we have done in our laboratory. I will just give you 2 or 3 quick examples, all right? So if you have a look at the literature, you will see graphene is basically a saturable absorber. So when you perform a Z-scan experiment, they will give a peak-like pattern. which says your graphene is going to be a saturable absorber. And what do saturable absorber do is, when you allow the light to pass through, they will not allow the light to pass through. So the output will remain flat. And when it crosses a threshold, suddenly your material will become transparent and they will allow all the light to pass through. Right? So which is going to be exactly the opposite of your optical limiters. In optical limiters, the material will remain transparent at the beginning. They will allow the light to pass through. Beyond a threshold, they will turn themselves opaque and they will keep that particular light output constant. All right? So a saturable absorber cannot be used as an optical limiter. So what we did is, we have taken a saturable absorber, right, and we have decorated them with different materials, and we try to invent the process of optical limiting from that particular material. What we did in our laboratory is, we have taken a zinc ferrite and we have decorated them with reduced graphene oxide, and when we excite them with femtosecond lasers, as you can see in the picture, right, the graphene, which was a saturable absorber that gives you a peak pattern, suddenly changes into a valley pattern, right, when zinc ferrite was decorated upon them. Because zinc ferrite is basically a weak reverse saturable absorbing material, right? And when you decorate them with zinc ferrite, the material switches their character from saturable absorption to reverse saturable absorption. What happens as a result is, they demonstrated optical limiting behavior, right? And impressed by this particular result, we performed many experiments on this particular system. Before I go for another example, I will give you one more example, right? What we have developed in our laboratory, right, was a silver decorated molybdenum disulfate upon a reduced graphene oxide system, right? So this is a graphene upon which I place microspheres of MoS2 decorated with, right, silver particles, silver nanoparticles. Right? What we observed in this particular material is, when we perform the Z scan experiment at different laser intensities with the different laser pulses, what we have observed is, initially the material showed saturable absorbing character. And when the intensity, pulse energy was increased and a Z scan was performed, the material turns themselves to reverse saturable absorption. And when we made a detailed investigation on that particular system, we observed that this reverse saturable absorption arises through a phenomenon called as two-photon absorption. And these two-photon absorption occurred in two ways. One is a sequential two-photon absorption, and the other one is a genuine two-photon absorption. Just to make you understand what is sequential and genuine two-photon absorption, in sequential two-photon absorption, what happens is, the electron absorbs one photon, they move to the excited state. They absorb one more photon and they move to the next excited state. Right? You call these as excited state absorption or sequential two-photon absorption. Whereas genuine two-photon is the process in which the electron absorbs two photons in the ground state itself and they move to the second excited state directly. Right? And when we performed Z scan on this experiment, we observed a very interesting switchover from saturable absorption to reverse saturable absorption through sequential to genuine photon absorption. Right? We have reported this particular work as the first experimental demonstration of a nonlinear theory. Right? In theory, right, this particular transition was proposed, but no experimental evidence was there to connect this particular transition. Right? In our laboratory, when we performed this experiment, right, we got this particular transition. I will just quickly show you, right, what has happened. Right? Imagine you have a material, I allow a light to fall on them. I give a small number of photons falling on them, a normal light falling on them. When a normal light falls, the electron will absorb the light and they will transit themselves to the excited state. Right? And since spontaneous emission is a quicker process, all those particular electrons which are excited will get back to the ground state quickly. You call this as a one photon absorption process. And when I increase the number of photons falling on the system, if I increase the total number of photons falling on the system increased, now what happens is that the number of electrons moving from ground state to excited state will be higher than the number of electrons moving from excited state to ground state. What happens as a result is that after some time, this ground state will get depleted. You call these as ground state bleaching, And this process is called as saturable absorption. All your electrons which are available in the ground state will be transferred to excited state. This is a one photon absorption, but still it is not a normal linear absorption. It's a non-linear process. Because in linear absorption, ground state depletion or ground state bleaching is not possible. Now imagine what happens if I give more number of photons on this system. When I send more number of photons, what happens is that those electrons which are available in the first excited state, they will start observing more photons, right? And they observe photons and they move to the second excited state. You call these processes excited state absorption process. And when you see that together, you see two photon absorption taking place in a sequential manner. So the system transfers themselves from saturable absorption to reverse saturable absorption. And this time reverse saturable absorption arises because of excited state absorption or sequential two photon absorption. Imagine still I increase the number of photons falling on my system, right? When this photon number increases tremendously, the electrons in the ground state will start observing two photons at a time, right? And they started, right, undergoing the process of genuine two photon absorption. By observing two photons at a time, they move to the second excited state directly. You call these processes genuine two photon absorption. Although this is a theory, no experimental evidences were available in literature. We recently reported this particular work in literature. And using this particular material, what we did in our laboratory is we have fabricated them as a simple, right, thin film, and we investigated whether this particular film exhibits any optical limiting behavior. You could see when the intensity of laser increases, initially the light transmits the light to go through, which means that this particular glass allows the light to pass through. It will allow the laser to pass through. But when the intensity of the laser exceeds the threshold, when the intensity increases, you see the light output gets saturated. Even when I increase the output of the light do not increases proportionately. They remain in the saturated level, right? So this gives you safety. And this particular material is now attempted to fabricate as an optical emitter based laser safety devices in our laboratory. Likewise, as a last closing note, I will give you one more example. When reduced graphene oxide was coated with gold ferrite, we observed another peculiar property called as broadband optical limiting. You all know that optical limiting is going to be a peculiar property for one specific wavelength. When gold ferrite was decorated with reduced graphene oxide, we observed this material, right, exhibited optical limiting behavior for different wavelengths of laser, which means that using a single material, you can perform optical limiting for different wavelengths, right? So at present, people are looking for the possibility of creating a laser safety devices using optical emitters. In the future, people will be looking for broadband optical emitters, a single material that gives me the provision of doing the optical limiting for different wavelengths. We demonstrated this particular work very recently, right, using gold ferrite decorated reduced graphene oxide, and we call it as broadband optical emitters, right? So with this particular example, I will just quickly go for my closing note, right? We have a diversified faculty community here. You may be working on different materials, right, in your research work, right? You may be working with semiconductors, you may be working with dielectrics, you may work with metals. What is interesting is when you put these particular materials in front of laser, they behave like a nonlinear optical material. And when you perform Z-scan experiment, you can understand what is the type of nonlinear optical phenomenon that is available within that system. And if your material has these particular reverse saturable absorption behavior, your material can be utilized for optical limiting applications. If your material has saturable absorption, can be used for Q switching like applications. And this opens a very broad, right, opening for material scientists, because with Z-scan, you can develop one application, right, on lasers. And that's give the broadest scope in research with laser photonics. So with that particular note, right, I will just say thank you, right, for listening to me very patiently. And if you have any clarifications or if you want to discuss with me regarding utilizing these laser facilities, you can mail me out, right? I will hand over the session back to the organizers. I'm welcome to have an interaction with you for the upcoming minutes. Thank you all so much for your patience listening.
Thank you, sir, for your insightful session and simplifying such complex topics like lasers and graphene applications in a way that was easy for us to understand. And we truly appreciate the time and effort you have taken to prepare and deliver such a well-structured and engaging presentation. Thank you once again, sir. Now we would like to open the floor for interaction. Dear participants, this is your opportunity to clarify your doubts and share your thoughts. We encourage you to ask questions and make the most of this valuable session with our resource person.
Right. I got one question in the chat box. One friend was asking, I could like to know the mechanism. Can you explain in proper manner? Right. I'm sorry. By 722, you are asking me the difference between excited sequential absorption and genuine two-photon absorption. Can someone give me more clarity on that particular question? Because by 722, I was talking about the mechanism on sequential two-photon absorption and genuine two-photon absorption. Yes, right. See, what happens is both these particular phenomena are capable of demonstrating optical limiting. Imagine if your material has excited state absorption or sequential two-photon absorption, what happens is, right, the material will absorb more photons and they will exhibit optical limiting. And when it is going to be genuine two-photon absorption, this process is going to take place quickly because two photons are absorbed at a time and they move the electrons directly to the second excited state. So if you compare a sequential two-photon absorption with genuine two-photon absorption, the genuine two-photon absorption is a very quick process compared to your sequential two-photon absorption process, right? And that's the difference that you have to keep in mind when you compare these two things. And what we have demonstrated with that material is, by theory, linear absorption should become non-linear absorption. So the connectivity is linear absorption becomes saturable absorption. And when I increase the intensity, this saturable absorption should become reverse saturable absorption, right? And when the connectivity between these two is, when a material becomes saturable absorption to reverse saturable absorption, it should pass through a process called as excited state absorption. It should undergo a sequential process and then only it has to move to genuine two-photon absorption. So this is the theory that is available, right, with the nonlinear optics, and we have demonstrated them experimentally in our laboratory. Hope I have answered the question to you.
Sir, I can ask one question.
Come again?
Can you hear me?
Yeah.
Yeah. Actually, how to identify or how to differentiate this is a genuine two-photon absorptions or a sequential two-photon absorptions?
Yeah.
Because the time calculation is we do not know. Because it is a fast process or slow process, then only we can identify. Then how do you say this is a genuine or this is sequential?
Yeah, I understand your question. Due to time limit, right, I have skipped some of the slides. I have not taken you to more deeper into the nonlinear optical phenomenons. Right, the basic difference between your sequential two-photon absorption and genuine two-photon absorption can be identified by performing Z-scan experiment, right, with different laser pulses. Right, your genuine two-photon absorption is a process in which, when the laser pulses changes, the non-linearity does not change. Right, which means that if I perform an experiment at 100 microjoule, I get some pattern. If I perform the same experiment at 150 microjoule, if the pattern remains the same. If I do the experiment at 200 microjoule, if the pattern remains the same. It means that the nonlinear absorption coefficient is independent of intensity of my light. Right? You call this condition as genuine two-photon absorption. But in sequential two-photon absorption, what happens is, When you change the laser pulses, say for example, I perform the experiment at 550 microjoule, I get some beta value. If I increase the light pulse to 75 microjoule, right, the beta value, right, will increase slightly, right? And when I increase, still it increases. Beta becomes a function of intensity. You call these processes sequential two-photon absorption. So by plotting a graph between nonlinear absorption coefficient, right, and laser pulse energy, right, if it is going to be dependent, you call that process a sequential two-photon absorption. And if it saturates, if it remains constant, you call it as genuine two-photon absorption. Hope I have answered your question.
Yeah. And one more question. So people are, I have seen some literature about 3-photon absorptions or multi-photon absorptions.
Yes.
So these photon absorptions also exhibit optical limiting properties?
Yes. Undoubtedly, all multi-photon absorptions can result in optical limiting, right? So instead of 2 photons absorbed by your material, if the material absorbs 3 photons at a time, optical limiting will take place very strongly, right? But what is interesting is these nonlinear optical phenomena, when you move from 2 photon to 3 photon, you have to move from third order to fourth order, right? When this order of nonlinearity increases, the possibility of observing that phenomenon will also decrease, because fourth order nonlinearity is a weak process compared to third order nonlinearity. Third order nonlinearity is going to be a weak process compared to second order nonlinearity. So observing 3 photon absorption, right, is even though possible, observing them in reality is practically less when you use lasers like nanopulse lasers. But with the invention of femtosecond lasers, attosecond lasers, now people started demonstrating third harmonic generation, 3-photon absorption, fourth harmonic generation, 4-photon absorption, and many multi-photon absorptions, right? Those results are coming, right, in recent times.
Thank you, sir. Thank you very much for your clarifications.
Okay, I got one last question maybe, right? Since the next speaker may join, right, at 7:30. So yes, the laser threshold, the pulse energy plays a very important role in this nonlinear optics, because nonlinear optics is the phenomenon in which the property changes with the intensity of light, which means when you change the intensity of your laser, the property also changes, right? So the pulse energy has a direct impact on the properties that you measure. Okay, hope I have given the answers.
Thank you so much, sir, for the clarifying the doubts. I also thank the participants for your active involvement in the section. The feedback form will be shared in the chat box. I kindly request all of you to fill out the form without fail, as your feedback is very valuable for us. So kindly fill the form.
Ma'am, shall I take a leave?
Sure, sir.
Okay.
So with this, on behalf of the organizing committee, I sincerely thank our distinguished resource person, Dr. T.C. Shabarigirishan, for sharing his valuable knowledge and insight with us today. I also thank our respected management, principal, heads of the departments and the faculty members, and all the participants for their active participation and support. We look forward to your continued involvement in the upcoming sessions also, sir. And thank you once again. Thank you, sir.
Thank you, ma'am. Thank you. Of course, I'm interested to attend the next session since I have one more commitment. Right, if I finish off, I will come and join. Right, thank you all so much for your patience listening. Right, if you want any clarifications, you can mail below. I wish you all a great success. Thank you.
Thank you so much, sir. So now we move on to the session 6 of day 3 of Atal Faculty Development Program, organized by Marthanam College of Engineering and Technology. It gives me immense pleasure to warmly welcome our next distinguished resource person, Dr. John D. Rodney, who has graciously accepted our invitation to share his knowledge and expertise with us today. His presence here adds great value to our FTP, and we are certain that this session will be highly insightful and enriching for all the participants. To introduce our esteemed speaker to the gathering, I now invite Mrs. Soni Meera, Assistant Professor, Department of ECE. Ma'am, please.
Thank you, Rashmi ma'am. Good evening, everyone. It's my privilege to introduce our distinguished guest, Dr. John D. Rodney, Research Professor in the Department of Advanced Components and Materials Engineering at Suncheon National University, South Korea. Dr. Rodney completed his PhD in Physics at Loyola College, University of Madras, and has worked as a postdoctoral fellow at NIT Karnataka and as an assistant professor at Annai Violet College, Chennai. His expertise lies in nanomaterials, electrocatalysis, and energy conversion technologies. He has authored more than 47 international research papers, holds a patent, and has received awards including the Best Oral Presentation at the Asia Pacific Forum on Renewable Energy 2024. We are truly honored to have you with us today, sir. We warmly welcome you.
Thank you, Professor. Thank you so much for having me here. I hope I'm audible. Am I right? Am I audible?
Yes, sir.
Thank you so much. Thank you so much for having me here. And thank you for this opportunity for letting me share what we are doing here and also help the other faculty members so that they can also progress in their research fields. So let me present my slide first, and then let's go on to the discussion. So can you see the slides?
Yes, sir.
Okay. Thank you very much. So I hope I'm audible to everybody. The topic that was proposed today for discussion is orthoborics for energy applications. But before going into that, I will just give us brief information on where I am from and what I'm doing. So I'm working in a university in Suncheon National University in South Korea. So it's a very basic university, not much advanced in any sort because it's an agricultural university. But the main focus is on environmental and energy-based applications has been going on right now. And this place where I am is very good with respect to different natural scenarios and different climates and so on and so forth. Anybody who is interested can also apply for postdocs and other research positions if you are interested in Korea, and also you can pursue your postdoctoral activities over here in the future. So moving directly on to the work. So let's first look into what this faculty development program is. I know that you would have gone through a lot of expert talks in the days before and in the days to come. You would have seen a lot of advanced research topics being discussed in this forum. But I thought I'll take this discussion in a different manner, even though I'm going to talk about the material advanced ways of analyzing a material and trying to understand different criteria. This FTB is mainly to develop the faculty in pursuing advanced research. So that's the core requirement of this FDP. So the title of this FDP is Advancement and Application of Smart Materials in Environmental and Technologies. So we can take it in two ways. One is metaphorically and also literally. We'll go metaphorically trying to develop a smarter material with advancements and also with advanced applications. So why am I emphasizing these things is right now in this energy field, if we take the energy field of production or storage or anything, we are confined into a very small area. We are not looking beyond certain materials. So if you see currently, there are advanced materials that is being researched right now. as I've given in the left side of my slide, you can see there is a lot of materials called single atom catalyst. You have MXenes, which has been trending lately, MOFs, which has been trending lately. You have borates, phosphates, orthoborates, oxysulfides, so on and so forth. You have high entropy alloys. There are a lot of materials which has been researched extensively. But are we pursuing those materials? That's a very important question. Are we pursuing some advanced or recently researched? For example, let's take HEA. Ion repellers basically was, let's say, they started and the first paper was published, I think, around 2005, which is basically 20 years ago, which is a new topic. But the amount of research that's been done is very less from our place, let's say in the southern part of India. So we have to think about the way we approach the research applications with respect to material selection, material development, and also for applications. And the reason I've given the right side of the slide is there are different energy applications that can be researched and are being researched currently. I know most of you would have been researching in these topics, like you have the solid state batteries, lithium sulfur batteries, zinc air batteries, supercapacitors, fuel cells, electrolyzers, solar cells, supercap batteries, LIBs, SIBs, and so on and so forth. But what is lacking? What is the reason that we are here in this FDP? What is the reason we have attended this FDP? Not to know what is the new material this guy is going to speak about, but to advance ourselves so that we can pursue or we can carry out much more advanced research in developing much more smarter materials. So in my point of view, there are two ways research is being carried out currently. There is exploratory research and also there's industrial research. So I'll just explain it in a very brief manner. Exploratory research is something that we are doing currently in a very minimalistic manner, where we are targeting to understand the material. We are not worried about trying to get the best efficiency out of it, but we are just trying to understand what happened, why did it happen. See, this topic, this discussion, the entire presentation today is, even though it's based on electrolyzers and like energy storage and production, but I want you to think in a perspective with respect to your material or with respect to your research field, so that you can progress your research in much more advanced manners. So we don't target efficiencies where we just target with respect to understanding a material. And what we do after that, we work towards deeper understanding the material, trying to understand the various phenomena that's going on. I hope that would have been the discussion with respect to different talks you had, with respect to what's happening in your material, why did it happen, how did it happen, why did I see that phenomenon, did this come, or what is this mechanism, so on and so forth. These are the things that we are much more keenly looking into. And there is a separate group of people. There might be people here also who are doing advanced industrial based research, where they don't target, see, even though they will understand the material also, the main target will be the efficiency, the output of higher efficiency. So they will design a material in such a way that they achieve the efficiency, so that work can be patented or they can do technology transfer. It should be commercialized. It will be done with respect to collaboration with an industry, so that they work together on something. But to advance your research, the reason for this FTP is that you have to also move further in advancing in your research. So to do that, what's the only way? You have to do both together. You have to design your work, or you have to work in such a way that you do exploratory research also, but also you combine a bit of industrial-based research. This is not only for paper publications, but also for your research labs, where your lab's focus not only has to be on one direction, it has to be on both the directions, so that you can advance further. That's what I want you guys to understand, so that you take to yourself at the end of this FDP, so that you can expand your research ideas much further. So there's one more thing we have to understand before going into it is, I feel you would have known about TRLs, or some experts would have spoken about the TRLs for sure. I hope so. So the TRL is basically technology readiness level. I don't want to go into it much further. There are totally 9 levels of TRL 1 to 9, which starts from basic observations to the final commercial production with respect to commercially selling the product. It can be your material, can be a product, it can be a device or anything or an idea also. So I divide this into 3 sections. The first section is basically TRL 1 to 3. The second section is TRL 4 to 6, and the third section is TRL 7 to 9. You see, you see that the main problem that we have, that I want every faculty to understand, is we are still, not everybody, most of us are still stuck in the level of TRL 1 to 3. We do basic observation. Sometimes we also select advanced materials, but still we do basic observation. We do basic understanding studies. We just give proof of concept. We just validate it and we just complete. We just move on to the next material. We don't do more beyond that. We don't think about extending it beyond that. This is where your work has to move beyond exploratory research to an industrial based research, where you have to move further. And I urge you after this FDP that you have to move further to TRL 4 to 6, at least till 7 is what you have to do, so that your work is much more usable, and it's much useful to others, and also it can be also in future can be commercialized after due process of the material. So I urge you to move beyond the first section and go on to section number 2 and also 3. This is very important. So we have to move beyond this one, and we have to go at least till TRL 7. That is the talk today that I'm going to share with you with respect to one of the studies that, one of the work that we recently did, and it's currently under review. And I'll share informations about it, even though I can't cover most of it. I want you to have it as a stepping stone for your own work so that you can progress further. So, yeah. So, last point before going into our work is, there are 3 things which I always discuss in all the talks that I go through. Is there are 3 core questions that will enable you to move further. Rather than sticking on to the first section, that is TRL 1 to 3, you can move further, and also making yourself better in the levels of 1 to 3. That is also something that we lack. That's also something that our students lack, that we have to push them much further to ask these 3 questions. What is that? What, why, and how. We have to, in every step of research, we have to keep on asking what, why, and how, which is very important, so that our work with respect to exploratory research or also with respect to industrial research moves much further. We give much more scientific evidences rather than just getting the data, plotting the data, and just reporting the data is not something that we have to do to reach the level of other advanced researchers level. This is what we have to do. Whatever research it may be electrolyzer based research, it may be solar cell based research, it can be supercapacitor based research, or crystal based research, whatever may it be. These things that we are discussing right now is very important, and I want to take it to yourself so that you can improve the students much further, and also your research in the days to come. So the question is what, why, and how. This is something that we're going to keep on asking in our work. Okay, so let me directly go into my work. As I said, the need for developing a material is very important. And to move further in your research, just thinking single dimensionally is not enough in this current stage. The days have passed by with respect to doing one section of research. What we can do to get a good output or to get a good paper out of your work, what you have to do, or a work to be useful for the society or to other researchers, let's think in such a way that when will I open a paper and read about it? When I get the information that I want. So if you're going to do a single dimensional research, for example, you're going to work only on HER. HER basically means hydrogen evolution reaction. OER basically means oxygen evolution reaction, or as oxygen reduction reaction. We'll get into it anyway. But if you're just going into one dimensional, let's say just one topic, you want to just focus on one, you make it as strong as possible. The science has to be very strong. Not only reporting, it has to have all the questions. Why did it happen? How did it happen? What happened there? Like every single thing has to be asked in every single section, so that you will find the answers, and that answers will become your manuscripts, and that will be much more advanced paper compared to the papers that we usually write. So what did we do? We went on a different way where we went for a three-dimensional approach where we want to develop a catalyst. A catalyst not only will be capable of doing one work properly, but it can also be used to do two works, not only two, but also three works, which is it can be used as a catalyst for hydrogen evolution reaction also. It can be used as a catalyst for oxygen evolution reaction also. It can also be used for an oxygen reduction reaction also. So why is this an advancement? See, this is an advancement is because you can pair up any two. If you pair up these two, you get the electrolyzer. When you pair up these two, you get the air battery. So there you bring in three different mechanisms where your material will be able to do three different processes in three different instances, which can be implemented for two different devices, which makes it completely energy efficient. It makes it cost effective because you don't have to develop different materials for different application. It simplifies everything, sustainability, scalability, and also durability. So this is one way of thinking. That doesn't mean you can do only one part of research. It is doable. You can do it. But again, I will explain in the upcoming slides where, like, how can you make it better? How can you make it wonderful so that you also move further? You also advance in developing very smarter materials when compared to the other materials that we usually do research upon. So before moving into it, we have to understand what's OER, what's HER, and what's ORR. And I think most of you would have already known about it. And anyway, we'll just touch up about it. So OER is basically of oxygen evolution reactions where your water breaks and you get oxygen evolution. And this is basically, we already know, like theoretically, the required potential to break a water is 1.23, whereas it never happens with respect to what theoretical value is. It requires an additional potential for this work to happen. That is based upon different parameters with respect to electrolyte, the ambient temperature or the pressure, and so on and so forth. There are a lot of the things that come into play, but let's keep it simple that an additional potential is required to achieve oxygen evolution reaction. So what happens is that additional potential is called the over potential, the additional potential required. The same goes for HER also. HER basically occurs theoretically at 0 volt, has to happen, but does it happen? No, that everybody knows. So it requires an additional potential over potential. And our work basically is the simple thing that we are trying to bring the required potential down. Same over here, we are trying to bring the E half-wave potential as lower as possible. That's the main requirement in all the three. So you see here, this is a different perspective. This is a different perspective. This is a different perspective. So how does a single material comes into play, and how does it enables? How does it work? Why is it working? Why is it better? That is the main question we have to ask ourselves when we are carrying out a basic research with respect to these applications. So, okay, anyway, this work was carried out here, but anyway, I'm just changing the way of approach. So, as I said, there is a question that comes like, why are we carrying out this research? That is the basic question. Why are you carrying out research that you are developing a material for the production of oxygen and also hydrogen? So I will just brush through the slides very fast because we have much more important slides later on rather than these ones. But right now, the fossil fuels are completely depleting. We know that very well. And we also know that you can see 5 years ago, were there these many EV vehicles, like electrical vehicles available in India compared to what you see right now? Like every household needs an electrical vehicle. That's what they are progressing towards. Why did it change? The government started moving towards cleaner energies. Why? Why so? There's always a reason behind it. And you can understand that the fossil fuels are depleting extensively and they are trying to achieve larger targets with respect to renewable energy. To do that, we have to rely upon renewable energy. So when you rely upon renewable energy, you have an abundant source of renewable energy. But the main problem is you can't completely use it. Let's take for an example, you have a solar cell in your house. Solar cell is being used extensively, and the amount of energy that can be generated and that can be used is extensive. But is it being completely used? No. the most of the energy that you get will go on grid to the government or to the main power plant, where it's not being used properly, where it can be converted. This renewable energy can be converted and stored in a very good way. So when we talk about storage devices, all we think about is what? Supercapacitors, batteries, and so on and so forth. But everything has a bottleneck. Everything has a limit for its storage capabilities. That's where hydrogen comes into play. Hydrogen doesn't alone come into play as let's say a storage storing capacity for the renewable energy, but also it comes into play as an energy production process also, where we will, if you guys are working on fuel cells, you will know that the hydrogen can be again used to produce energy. And why is it very clean and why people have to think about this is because when you break the water, you get hydrogen. I'm saying in a basic manner. And when you try to burn hydrogen, you get water, making it as green as possible. So even though batteries are being highly researched currently, and the battery vehicles are being highly used currently, electrical vehicles and so on and so forth, the hydrogen's time will come. That is why the government of India has initiated something called the NGHM, which is the National Green Hydrogen Mission. I think in 2023, if I'm correct, in 2023, it was proposed in the cabinet. And right now, a lot of funding has been pushed towards the development of materials, devices, plans, and so on and so forth for the production of green hydrogen. So what is green hydrogen? We'll come into it anyway. But it's been pushed a lot. But again, see, when you look into that criteria, you will think like, okay, government is pushing a lot of money with respect to development of devices and so on and so forth. So how to even approach and get the funding? See, even developing a material which can bring the required potential down is a highly breakthrough research in terms of hydrogen production. For example, let me say I am developing a material which will produce hydrogen. Let's say it requires 1.2 volt of energy potential to produce, let's say, 0.5 kilograms of hydrogen in 1 hour. Whereas, let's say you are developing a material which requires 1.15 volt, which is not a huge difference, right? Only 0.05 volt difference to produce the same 0.5 kg in 1 hour. So when the required potential is gone down, even at the smallest level, that brings the required cost down for producing a hydrogen, which is a very highly breakthrough one. That's something we are overlooking when we are doing research. We are the problem is we are looking at some advanced stuff, or we are not looking at anything. We have to look in a very progressive manner so that we can do very good research with respect to a material-based research, also a device-based research. So the positives and negatives of one hydrogen is already well known, as I've given here. I don't want to go into it much, but it is highly, highly usable. And we are, as electrolyzer-based research community, we feel that hydrogen will come into play for sure in this world. It will surely come into play in the next 5 to 10 years, replacing batteries, not mostly, will surely come into play because it's highly usable with respect to even powering up huge cities also, if need be. So in that, there are different aspects where hydrogen can be used. As I said, it can be used in fuel cells to produce energy, or it can be we can use a device to produce hydrogen. So the aspect that we are going to look into is basically how to produce hydrogen. That's my talk today. So this is the main thing. So why are we doing this research? What is the purpose? What is the different aspect that's present that I'm carrying out this research? Such questions have to be asked by yourself or like by your students, so that they can carry out a much better research. So there are different ways of producing hydrogen, which is like steam reformation, acid hydrolysis, photoelectrocatalysis, and water electrolysis. There are even more, much more, which I have not added here. But you see, the top two over here is being currently used as we speak. But the problem is the byproducts and the harmful gases that's being produced outside in the span of producing hydrogen. And the purity of hydrogen is also not that great. Coming into photoelectrocatalysis, it is a very good approach to produce hydrogen because it's completely green. It's completely green, but the main problem is we require more hydrogen. We can't wait for it. We need more hydrogen. We need it fast. We need it more purer, and we needed it at every time, not only in the day, not only in the night. We need it at every time whenever it's required. So that's where it's lagging, where the production rate and the amount of hydrogen that's being produced is completely low. It's completely low when compared to an electrocatalytic water splitting based application. So that's where electrocatalytic based water splitting comes into play, where you have such devices, which we will again look into it in our slides. You have anion exchange membrane based ones, and you have proton exchange membrane ones, and also you have hybrid types and so on and so forth, where extensive research is going on currently, and India is slowly moving. Researchers in India are slowly moving towards it, trying to research materials and also devices based on hydrogen. And lot of papers are being published from India, which I also strongly urge the other researchers and professors to look into the new the hydrogen production field, which might be a very good thing that you might do with your lab and your students, because it will bring in good projects and you will have good outputs, and also it will be good for the community in the next 5 to 10 years. So the different types of hydrogen. Hydrogen is colorless and odorless, we know that, but it is being colored, and there are even a lot of colors which is being divided into, but we are going to see only some sets of it, whereas the main concept over here is green hydrogen. That is what the Indian government is pushing pushing right now to achieve. There's been a lot of criteria that's been proposed to achieve this green hydrogen. Why? As I discussed earlier, we can achieve it through electrolysis using renewable energy, so that the hydrogen that is produced is green. So it's pure, and it's using renewable energy, so it's called green hydrogen. If you use the nuclear energy, it becomes pink hydrogen, and if you use steam reformation or something, it's gray, and other gasification process or something, you get blue hydrogen and black or brown hydrogen. So the main thing that we will be focusing is on green hydrogen, and I also urge everybody to work in such a way that you work towards the production of green hydrogen. So before moving into the topic, let's see a couple of advantages, and we have already covered the advantages. As I said, through electrochemical water splitting, you don't require high temperature or pressure or anything like you needed steam reformation, or no greenhouse gases being produced with respect to the same as in steam reformation or the acid hydrolysis or something. You get the purest form of hydrogen. You get 99.99% pure hydrogen, because you sometimes at extensive productions you have some oxygen crossover happening in the membranes, and that might slightly contaminate the produced hydrogen, but it's not extensive, and it can be easily be like, let's say, removed, and you can get much more pure hydrogen. And as I said, the hydrogen is when you break water, you get hydrogen, and when you try to burn hydrogen, you get water again, which makes it cleaner. So what happens inside? That's the small thing. We look into it, and we'll go into our much more in-depth discussion. What happens is water, when you apply a potential, what happens is in the anode part, what happens is the water breaks, and you get oxygen, and you get 4 protons and 4 electrons, which is being used when you're doing water electrolysis, I'm saying, which is required in this section. And that, when combined with 2 electrons, gives you 2 hydrogen evolution. So there are, as I said, you can do single dimensional research where you can only focus on this region, because hydrogen evolution is very important. But there is a huge problem which you have to look into, is that is OER, which people try to always look don't look upon. They just look over it and just go into, okay, let's design a material only for HER. The problem is OER is the main problematic section in a water electrolysis system, because in an alkaline medium, you don't have the required protons always present for the hydrogen evolution reaction, whereas in acidic it's always present, and it's very good in that. Whereas in alkaline system, it's not always present, so that the OER has to work out properly, so that it will produce the required protons that is needed for this reaction. So if this lags, as I said, the over potential is too high, what happens is the hydrogen evolution reaction also will lag, where you won't get the zero based output, you will get and over potential again. You see, you will also get an over potential here because this is directly implemented because of this section over here. So right now, everybody is looking into bifunctional catalyst, where a catalyst can be used for both OER and HER. But I strongly urge that please don't overlook the oxygen evolution reaction, because this step is also very important. If Elon Musk also has told that the reason he's not looking into hydrogen evolution or using hydrogen as the main source is because we waste energy in this part over here. This waste of energy is a huge loss with respect to his concept. And if need be in the upcoming years, because every single work that is being done right now, let's keep it simple. In terms of electrolysis, electrolyzer, what are we doing? All we are doing is trying to develop a material that will bring the required potential down with respect to OER or with respect to HER. If it brings the required potential down as close as possible to 1.23, it makes it as a better catalyst, so that you have much more higher production of oxygen and also hydrogen, making it as the best catalyst possible. And that is also the durability factor and so on and so forth. But this is the main thing that we require. We are designing a material so that we can bring the required potential down. That's where the advanced materials, as I said, which is being currently researched, like MOFs, COFs, chalcogenides, and you have perovskites, or you have, let's say, borides, phosphates, borates, so on and so forth. Everything comes into play, and that has been useful in carrying out advanced research with respect to developing an electrolyzer for producing hydrogen, which is very important currently in India, because there is a huge necessity. Such research has to be done in our country right now, because we all are working on supercapacitors and batteries. The required push has come currently that we have to look into hydrogen production, electrolyzer, and also maybe also into fuel cells, and also into storing hydrogen using hydrogen storage based applications. So moving into the one more topic, which I may or may not touch into in this discussion, is the Zinc batteries. I said we are working on OER, HER, and also oxygen reduction reaction. When we pair these two up, we get Zinc battery. When we pair these two up, we get the water electrolyzer. That is clearly seen here. If you need to understand more about the internal mechanisms and the basic chemistry that's happening in the system, I strongly urge you to go and study MTM Cooper's Fuels and Sciences book, which is very good to understand the basic electrochemistry of what's happening inside, where this one graph gives you a clear picture on 2 or 3 different applications that can be done. As I said, when you pair up this part of this part, and when you pair up this end, you get to do your work on an electrolyzer. And when you pair up this end over here, this is oxygen reduction reaction, and this end over here, hydrogen oxidation reaction. What happens is you get fuel cell. When you pair up this end and this end, that's ORR and OER, you get air batteries, storage devices. So you get different versatile options of developing different devices on a single material if need be. So I also again urge you not only stop in one section, move further, try to test it extensively, see like, can it work out? Could it work? Like if you get a data, try to understand why and so in that manner. So in that way, we'll also see Zinc batteries, which is currently being researched and also being somewhat being used right now with respect to in small areas, like some grid backups and hearing aids and some R&D based electrical vehicles, but not extensively, whereas lithium-ion battery has been researched extensively. But why I am urging you to go into Zinc batteries, because developing a lithium-ion battery, the amount of chemical cost that you have to bear upon to get the required source materials to develop it, and also you need a very clean and an inert setup to assemble the cells and also to evaluate them, which makes it completely difficult for us doing research in our colleges and stuff. If we have the facility, it's well and good. If not, we can look into something called Zinc battery, where the required chemicals or the required precursors are much cheaper, And we can also assemble such materials in ambient conditions. There's no need for inert or anything. It's completely eco-friendly, and still, okay, fine. It's not as good as lithium batteries, but you can carry out very good research with respect to developing a material that can one day replace lithium and battery. So how does it work is basically we will look into this part if time permits. We will look into zinc air battery, a rechargeable type zinc air battery, both liquid type and also quasi type, which I'll say why when you go into that part. While discharging, what happens is oxygen, the overall reaction is basically with the zinc metal and the oxygen reacts and you get zinc oxide. That is where a discharge of energy occurs, and your energy is being produced out. And while charging, what happens is that is dissociated, and the zinc is going back, and the oxygen is being evolved. So what happens here is you have reduction reaction of oxygen, and you have evolution. So these two mechanisms govern the zinc batteries, and we will look into in developing a material and evaluating a material in an advanced manner, so that it's a very smart way of developing a material for such diverse technologies with a single material that can with a single material that can achieve 2 different devices and 3 different mechanisms. So in that way, we'll go and look into the work itself. The work which I'm going to use to explain to you on how we can approach our research. It may be anything, an electrolyzer, or you may be a supercapacitor, or a battery, or a supercapacitor, or anything. But I'm just going to give you a small idea on how you can advance your research in such a way that you can push your research from the TRL 1 to 3 level to a TRL 4 to 7 level. And also in that 1 to 3 level, what we are lacking currently is we are not asking the proper questions. We are not asking the proper questions. We are just developing materials, reporting it, which is not good. We need to understand and ask questions, which I am urging you, everybody over here, to push your students so that you can also get wonderful outputs in your works in the days to come. So the work is basically fluorine-mediated coordinate engineering of iron-doped nickel orthoborate as a trifunctional catalyst, which will be used for both AEM-WE, which is the AEM water electrolyzer, and also a rechargeable zinc air battery. As I said, the zinc air battery section, if time permits, I'll go extensively in it. But if not, I will try to just brush up on it and conclude this session. As I think the time currently is 11:40 for me, which means we have some 40 minutes or so. Okay. So, as I said, let's just forget how we completely work on how we do our research. When we take an idea, the idea is already been set. You understand? So your plan is to develop a material. That's the basic plan. Your plan is to develop a material which can be used in 3 different mechanisms based for 2 different applications. First of all, you're going to look into water electrolysis. First, the main thing is to develop a material. So as I said, we can brush and go into different materials and different classes of materials, different families of materials. Whereas in our work, I've selected the orthoborates because boride-based materials is being researched extensively, whereas orthoborates are not being researched extensively in the field of water splitting or in the field of zinc air batteries. So that is a basic reason that this material was selected. So our approach is always, even though we can do advanced works, we have to keep everything simple as possible, so that, as I said, our work not only has to be exploratory research, it also has to be commercializable. Maybe if the output is very good, it should be commercializable so that we can push the material further. So that is a basic necessity that you have to think while developing a material. So let's say you select a material of one family, like I've selected the orthoborates. The reason that we selected orthoborate is basically we know that the BO3 minus framework is a very stable framework, even in harsher conditions. I know very well as an electrolyzer-based researcher, who works on the production of hydrogen and also storage applications, we know that the water electrolysis is a very harsh process, where it's a very harsh process which puts too much effort on all the aspects, on the lattice, on the planes, on the morphology, on the material, on the chemical bonds, and also on the coordinates also, even on this bonding nature of the material, where it is well known that the material tends to alter itself while the mechanism is being processed to achieve the best um, setup to produce hydrogen or oxygen. So in that way, we know that BO3 is a very strong setup. So we wanted to use it. So in that way, what we did is we decided on developing nickel orthoborates. The nickel orthoborate development, there are so many ways we can develop nickel orthoborates. There are so many ways, and there are even more trickier ways where you can do the production of nickel orthoborate. Whereas what we wanted is to have a very simple way of producing it. So what did we do? We just added the nitrate salts of nickel. Only for nickel orthoborate, I'm saying, only for this one. We used, it's given over here, the nickel nitrate and the boron source. And what we did is we stirred it, and the boron source was added dropwise while it was at 100 degrees Celsius for 2 hours, and it was dropped in a very sequential manner, in a proper manner, where we added only 200 microliters per iteration. And what did we do is we gave a gap of 30 seconds in between each addition. So in that way, we added the boron source into it, and we then left it to stir for 2 hours continuously, because we wanted it to properly react and form the orthoborate system. We didn't purge any argon gas or nitrogen gas or anything into this into our solution, because we wanted the oxygen to be present there so that we can get a proper orthoborate system rather than a nickel boride. So what happened in that aerated solution, we finally developed nickel orthoborates. Now, what did we do is, we know that iron has a very huge role in terms of oxygen evolution and hydrogen evolution. But we also know that there is a certain percentage after which iron will inhibit the activity completely. So what did we do? We went on 3 different concentrations, and we tried to evaluate the material, and we found out that the lowest concentration was the best possible option. And we had the iron doped nickel orthoborate, where the iron is replacing the iron atoms or replacing the nickel atoms, and we get still a stable system, which I'll show you in the later half. So then, as I said, we wanted to keep the work as simple as possible, because we wanted to do an exploratory research first. Try to explore the material, try to understand what is going on, what is happening inside, and why is it making it better. We know we have nickel orthoborate right now. We have iron doped nickel orthoborate right now, the best ones which was selected. And we wanted to etch the surface. So the plan was to etch the outer surface of our material. So we brought in fluorine as an etching agent. In this same process, 5 millimole of fluorine source was added to the system. And what happened is, we planned on bringing the fluorine. Because of the temperature being present, we thought that this fluorine will etch the surface, exposing more sites, more planes, so that it enhances the activity, because we know disorderedness and defects give about good output with respect to OER and HER. So this was the basic plan that we had. So with that, we went on further. Now, the plan was set, the metal was prepared. The same thing will be done by you also for your applications, whereas we have to evaluate what happened. This is where the exploratory research, the section of 1 to 3, TRL 1 to 3 should occur. So what did we do? We started evaluating. So when we started evaluating, we understood that we achieved what we wanted to achieve, as you can see, but beyond a certain percentage, NFB3 is basically the third level of iron doping, 2 is basically second level, One is basically the first level of doping. This was the best material that we had. This is the core material, this is the NB, nickel orthoborate, and this is the fluorine incorporated one. So when we went with respect to more iron, what happened is we found one peak over here, which is Fe3O2 peak, a separate impurity peak came upon, which we don't want. We just wanted to alter the system. We don't want to change the entire phase. So what happened? We stopped in that NFB3. As I said here, we only checked for 3 different doping. And then to the best material, what we did was we did the fluorine etching process along or simultaneously in while we are doing the synthesis. So what happened with respect to our survey and with respect to our plan, the same thing happened. Compared to the nickel iron doped nickel orthoborate system, more planes were exposed with respect to fluorine incorporated one. We also saw a shift in the peak where again that also suggested that the surface has been extensively altered because of the incorporation of fluorine. But we have to ask the question now, how did the fluorine do it? What happened really there? And will this give a good output with respect to our requirement? So again, we are going into the exploratory research where we are moving further, checking the usual stuff that we always do, that everybody does, that we move into SEM and we see that the morphology doesn't change much because we know that it won't change because we are trying to just replace some atoms, not extensively, in a very small manner. And also we are bringing in fluorine in a very small manner so that the surface might be etched slightly, and which can be seen in this section when compared to the shapes that been present, that we can see that's a very, very slight change in morphology. But what happened is in the EDAX that we did in SEM, we thought we will not see fluorine. So this is the steps that we will have to do in an exploratory research. So we didn't expect the fluorine to be there, but the fluorine was present. Again, we know that the EDAX of SEM is not that supportive in trying to understand on very small amount of metals elements being present. So what we did is we want to confirm like what happened. Is the fluorine still there? Which means if the fluorine is still showing up, which means it's not physically acting upon the material, it's also chemically bonded onto the material, which is completely different from what we were expecting. So we move further. The TEM also confirms that the TEM based SEM mode EDAX color mapping was again done, and we found out that the presence of fluorine is again still present, which is confirmed in TEM also. The plane indexing and all the things which we usually do, right? We compare it with XRD and stuff and try to understand where this confirmed that the phase formation is proper, but still this was bugging us a lot. This is where we are asking the questions like why, how, and how, like what happened there. This is the step where most of us usually skip. What we do is we don't think about checking if fluorine is there. We always skip this step where we know that we want to develop Ni, Fe, B, and O. So we just evaluate these things. We never think about the presence of fluorine. Always, it's very important trying to understand if maybe there is a residue from your precursors of even though you've washed and cleaned your material, if it's still present there, there's a huge possibility that it's chemically bonded into your system. So now the question comes again, why did it happen? How did it happen? And what is the output that we're going to get because of it? Because we thought only nickel and iron is going to act upon in our system, because we know very well with respect to the Hubbard values that the nickel has much more better affinity in an activity, followed by, I think, cobalt and iron and copper. So in that way, we selected these things. But now this is a different thing that we evaluated. So what did we do? We go for the next well-known thing that we usually do, that's XPS. So spectroscopic studies is a very good thing to understand what happened in the material. Now, again, as I said, the main problem that we have is we always report the data. We perfectly report the data, but we never try to explain or try to understand what's happening inside. Because see, in this research, we didn't do any huge gimmicks or something like bringing in a very huge doping, or we didn't do like a very huge modification or a big heterostructure, or trying to merge two different materials to get a very good output or something. Nothing at all. It's a very basic orthoborate system with iron present in the system. We just brought in fluorine, and now, even though our plan was to work on nickel, iron doped nickel orthoborate, now the entire work has changed. With respect to the flow of work, what happened is, now the question is, what is fluorine doing there? What is fluorine is doing in my system, and how is it making the activity better or worse? That is the question. So in the XPS, we evaluated the nickel section, and we found out that you can see that two oxidation states are present in the normal system, whereas when the fluorine comes and it alters the section, and we can see there's a shift and the oxidation state changes, whereas the 2+ oxidation state still is present, whereas fluorine's activity is clearly seen with respect to in the nickel section, where the nickel is being altered substantially, which has been observed over here. Well, still we don't know how and why, but we know it's happening. When we checked upon iron, we understood that the nature of oxidation state is still present, but there is just change in oxidation state, that the depletion of 2+ oxidation state and the increase in the 3+ oxidation state, like increase more of 3+ oxidation state, because the coordinate chemistry is slightly changed in the system. We understand that that's what has happened inside, but we still don't know why. The question is, the reason we are looking into nickel and iron basically in the beginning is because we know, again, that, as I said, because of the Hubbard values, I think nickel has around minus 4.0 electron volt or something, that much affinity in enabling a reaction. Whereas we know, because fluorine is bonded, we know that chemically it's bonded, but we don't know how and where and how and what it's doing. We are trying to understand on which one it's sitting. So through this, we can vaguely understand that maybe the fluorine is bonded to nickel more. That may be the reason, because there is much more higher number of nickel atoms present in the system when compared to the iron. Maybe because of that, or it has much better affinity in enabling such reactions. But we also can see that the iron has also been altered. So we can't conclude that the nickel is being bonded to fluorine just by vaguely trying to understand XPS. This is something that we have to understand clearly, that a very in-depth discussion with respect to spectroscopic studies is very important. See, I'm not going much deep into it. We can talk for hours and hours about this topic in terms of only this graph itself, but I don't have the luxury of time over here. So I'll move much faster over here. But your spectroscopic studies has to be discussed much further. The question is why? Why did this happen? Why such an oxidation state is substantially being shifted in the nickel? And if only nickel is being altered, then why over here, when the oxidation state is completely being changed, altered, even though nickel is being altered? So we can't come to a conclusion on what is happening in the system. Is it good or bad? We still don't know. But what is happening? That's very important in exploratory research. This is what we are lagging in our discussions in the TL 1 to 3. All we do is just report. A moment, please. Sorry. So all we do is just brush through what's happening, like what is the value that you got and what did happen. We are not looking into, is it satisfying certain rules? Is the amount, the concentration of oxidation state is varying? Does it imply on something that has happened to a material? Such discussions are completely missing, which is the advancement that has been required from us to do a very advanced research. So moving further, we can see that the BO3 also, the boron B1S, the B1S is also being slightly altered because of the fluorine being attached to the system. And we can see that one good thing is that the BO3 framework is still stable. It is distorted with respect to when you bring about fluorine. But what happens is it's still stable. That means that the framework is still withstanding, and that might be a good thing for your applications. And the oxygen states also can be seen over here, that you still have the metal oxygen bond and the boron oxygen bond. There, boron oxygen and metal bond, which is still present in the similar fashion, whereas the vacancy is being slightly altered, which states that at some particular points when there is BO3, that's you have boron and you have 3 oxygens, there is a possibility that you can have a singular vacancy that might be induced by the uh, inclusion of fluorine. Because we brought about iron, there is still some vacancy in the system, but because we brought about fluorine, there is also an increase in the vacancy. This is a small understanding that can be extensively discussed by us in our works. So these things we understand from the spectroscopy studies. Now, what happens is we still don't know, or we still can't prove just from the XPS and from your let's say the SEM or TEM or your the STMs and other modes, you still can't prove that fluorine is bonded to the system. So that's where we go into much advanced characterization facilities that is actually present in India also. I strongly urge you to look into it and try to use it. That's the X-ray absorption spectroscopy. Again, this is a vast ocean that can be discussed, where I'll keep it simple and fast because I'm just losing time over here. We tried to understand the bonding nature, and the main thing that we did here is we wanted to prove that fluorine is really chemically bonded to the system, because we are still asking the question why, how, and where, and what is happening, where is it bonded, is it really altering the system, is something that we want to know, because that will help us to understand the output that we are getting with respect to an electrochemical water splitting. For example, there is a change in potential. We just can't report saying, okay, fine, I doped iron, there is a change in potential, so I'm getting better value. This is not the proper way of doing it, where we have to give a proper scientific reasoning and proper scientific evidence on what's happening inside. So in that, we do XAs over here, and this is XA NES, and you have the EXAFS over here. What we can see is we will compare the nickel site and the iron site, mainly because that's where we have the doubts on where it is bonded and which one it's altering. Is it altering the nickel and is bonded to the iron, or is it bonded to the nickel and it's altering the iron? So this is something we want to know. So you can see over here, we did the nickel at first. So we have the reference data of nickel foil and nickel oxide, and this is the nickel data from our material. You can see that we can confirm through the white line section. This is called the white line section, where it confirms that there is presence of NiO bond, but not a separate bond, and there is no postage that's been observed here. So, but rather there is a pre-edge that's present over here. Pre-edge basically confirms that there is an alteration in the symmetry, in the coordinate. That is, you have a nickel atom. Nickel atom is known to be a tetrahedral based system, where it's bonded to 4 oxygen atoms, which is in turn bonded to boron. So this is a known thing. So we know if it's a tetrahedral structure, which is actually how a nickel oxide is, that's our reference, it should be, there shouldn't be a pre-edge, it should be like this. Whereas in our system, what we got is a slight pre-edge, confirming that this tetrahedral system has completely altered. In what way, we still have to prove it, but we confirm that this system is being altered slightly because of the inclusion of fluorine atom. So here also in EXFS, we can see that the nickel atom confirms NiO bond. Further studies can be done with respect to bond angle and so on and so forth, which we haven't explored upon, but we can be done. We just are much more focused upon is nickel being altered. And then we did the contour-based studies based on the EXAFS. Based on EXAFS, we did the contour study where this is the nickel foil data with this contour area states about the nickel-nickel bonding, and this area specifies the nickel-oxygen bonding, whereas we can see that the nickel oxygen bonding is slightly shifted to the higher region, and also there is a huge bonding nature which is being denoted here, which is being shifted much further, which is not really a nickel oxygen bond, which confirms that it's a different bonding nature. So from this we can assure that the nickel is the atom that is being bonded to fluorine. This contour area has been achieved because of nickel bonding to fluorine. And we can also confirm that the nickel oxygen bond is still present, but it has been altered, as you can see over here. So we still have to find out what has happened. So through this, we just confirm that this is happening. So such advanced studies can be done to understand, to do an exploratory research on what is really happening in your system. So similarly, we had the doubts on iron also. Now we tested the iron. The white line confirms the presence of FeO bond, not precisely FeO separately. Whereas in an FeO, a pre-H should be present with respect to FeO iron oxide, whereas the pre-H is still present over here, but it's slightly altered. It's slightly altered, confirming that the fluorine is affecting the Fe, but it's not completely altering it, which means its nature is still present, but the fluorine is affecting the system. We know that it's highly electronegative, fluorine, so it can alter its surrounding atoms also, but this confirms that the nickel is being the one that is bonded directly to the system, and iron is just being altered. And as seen over here, this confirms that there is no separate bonding nature, only a slight shift in the contour diagram that we got, and there's no Fe-Fe bond, which means we don't have iron as a single metal anywhere. We didn't find any Fe0 in XPS also, confirming iron is not sitting alone or without being bonded. So it is FeO bond. It's in currently in this state, FeO and B based bonding with a slight stress on the bonds because of the electronegative fluorine. So this gives us a clear understanding that a single atom, we don't have to do extensive high-level doping and stuff and so on and so forth to bring about some advanced studies. A single atom inclusion into your system can bring about high changes to the system. Now, still, we have the understand on how the coordinates is being changed and to what way it's been altered, which will be answered. Before that, we have the NEXA-FS, the near-edge X-ray absorption fine structure, where we look upon the 1s states, all the 1s states, which is the fluorine, boron, and the oxygen. So when we evaluated, we can see this is a happy thing for us, because without this bond, this peak over here, it completely rules out the presence of fluorine in our system, which means it's not chemically bonded to our system, which would have completely destroyed our work. But through this, we confirm that the fluorine is bonded to a metal atom. And which metal atom, again, we know. This confirmed the presence of fluorine, giving us a strong evidence that the fluorine is really present in the system, chemically bonded, altering the system in all its nature. The boron also was confirmed, and the small perturbation also confirms a slight alteration because of the fluorine inclusion, and also the OKH study also confirmed the presence of the metal oxygen bonds, and also the pre-H confirmed the metal oxygen bonds, and the main H confirmed the boron oxygen bonds. So which was confirmed, and it completely satisfies our work. So to answer the next section of where it is bonded and how it is bonded, that's where we brought in the use of DFT through VAST program. So what did we do is, it's again a vast research area where I'm just going to brush up in the top just to give you an understanding, because I want every faculty over here and also your students to move much further, asking such questions, bringing in new characterization options, new modeling options, new evaluating theoretical options, and new device options to answer your questions, making your work and your project much better and better. So we kept on asking the questions. Still, the question is how it's altered and why it's altered. As I said, the bonding nature of nickel is shown over here. This is a pure structure. This is nickel orthoboric structure with iron being doped in a small concentration. You can see iron being present in a very small concentration compared to the nickel atoms. So what did we do is we brought in a fluorine atom, and we didn't attach it directly to the nickel source, because we still have to find out, is it really attaching to the nickel? So we kept at the minimum distance, and we did the optimization process, and we figured out that the fluorine atom, because of nickel's affinity, goes and gets bonded onto the nickel atom, which again is being proved experimentally by the spectroscopic studies. Now, again, as we speculated, what has happened is the bonding nature, the coordinate nature, the environment has been altered. As you can see, the zoomed image over here, it should be 4 oxygen atoms. Whereas what happens is it becomes 2 oxygen atoms, and the nickel atom has been pulled out of its nature. So you can see that every single thing that we have experimentally tested and evaluated is being proved over here, stating that because it's being pulled out, this is altering the planes and forming defects, which we saw in the XRD and other things. And this fluorine bonding was checked through XAS, and it's proved over here again. And we can see that the coordinate is changed. Again, we saw it in XAS that might have happened, which is proved through DFT, that the tetrahedral nature is gone and changed to not a perfect trigonal pyramidal nature, because a perfect trigonal nature has to have 3 oxygen atoms with a atom in the top, whereas this is a distorted trigonal where you have a vacancy. As you saw in XPS, there is a vacancy present in the system of oxygen, which actually will alter our mechanism, as we will see in our system. This is a DO studies. I'm not going into it because I'm losing my time over here. So what did we do? We still wanted to understand why is fluorine doing it. I needed to prove that nickel atom is being altered, which is being proved. And we did a charge density difference study, and we found out that because of its electronegativity, this, you can see over here, the nickel atom is extensively being altered. The energy is being altered, and also the surrounding nickel atoms and boron and oxygen atoms, all are being altered. Also, the iron atoms. This is something that we saw in our XPS and other thing, that iron is also being affected. This is called a remote ligand perturbation, where remotely the iron atoms are being altered. So to confirm, we did the Barder charge analysis, where we tried to measure the charge of each atom in a normal system and also in a fluorine system. We found out that the charge of every atom surrounding it is at least being altered in a very slight manner, which confirmed our theory. And we confirmed that adding a small amount of fluorine completely alters the material's activity. This is a very important thing to understand. Now the question comes out, like, how does it have an impact on our electrochemical system? So I'll move much fast over here. We have the EIS when we confirm that the resistance, solution resistance is lower and internal resistance is much lower. The surface area is altered, as you can see, with respect to NFB1 and FNFB1, fluorine and without fluorine, it's been completely changed with respect to a substantial difference that is because of the inclusion of fluorine, not anything else. We did the electrochemical assessment with respect to hydrogen evolution reaction. Now, again, the question is here. Every time what we do is we just do electrochemical assessment. We just say, okay, in the 10 milliamp region, this is what I got. This much over potential is what I got. My metal is better. Now, the question is how and why? Why did it happen? Why is it better? We know the fluorine altering the system has changed the material, but still the question is how and why did this happen? So we have to answer it through mechanistic insight, where we need to evaluate the Volmer-Herovsky pathway based on the TAFL values that we got. What we do is we go on to evaluate theoretically, trying to attach hydrogen atom into the system, and we find out its Gibbs free energy and its adsorption energy. We can see that just by bringing in a fluorine atom, the amount of adsorption energy has changed. The nickel is not getting involved in the reaction, whereas iron is directly getting involved in the reaction. And the Gibbs free energy is around 1.3 or something. Sorry, 0.3 or something. Sorry, 2 or something. I'm sorry, I don't have the exact value here. And it is very good because we know the best material for hydrogen evolution reaction is platinum, which is minus 0.09 electron volt, which is very close. It's still not great because just one atom itself is substantially improving the activity, in at least bringing it as closer possible, making the mechanism much better. I'm not going deeper into mechanism as I'm losing much time over here. Everybody knows the Volmer-Hevrosky. We did all the required studies. All the radicals was tested, and only the hydrogen is reported over here. But we evaluated every single step, and it's been reported. And we have extensively discussed on how the atom is making this happen. So as I said, the adsorption energy is changed, the Gibbs free energy is changed. I'm sorry, 0.17, 0.172. So this is what we got. So this is again proving that iron is being altered, because here also it is working upon iron, and here also it's working upon iron. It's been bonded to iron, but then the energy required is changing completely. So why did this happen is because the ion is being altered remotely because of the inclusion of fluorine, which is bringing about such an activity, which is extensively to be discussed. This is what you get when you start asking the proper questions in your work, not only water splitting, in all other works. Same thing was done in OER. We evaluated the material, and we found out that the Tafel mechanism, and we thought that this might be an adsorbent evolution mechanism or a lattice oxygen mechanism. But the problem is, we need to prove that it's adsorbent evolution mechanism, because we felt with respect to the Tafel value that we got, it should be an AEM process or an LOM process. But what happened is, when we started evaluating it, we stumbled upon and found out that because of the vacancies present and because of fluorine is being present in the system, we didn't get an LOM process or an AEM process. What happened is we got something called the intermolecular oxygen coupling process, where two different sites involved in the reaction. Because we know very well, if you have AEM process, you have water, then you have OH, then you have O, OH, and O2, a four-step process, where for LOM, this step will not be there. Whereas in this, what happened is this step became O plus OH, where two different radicals worked upon in our system, and which led up to get us a very good activity. So when we don't ask the required question, what happens here is we will just report it by saying that this is LOM process or this is AEM process, without clearly understanding that a different mechanism occurred inside the system. So it's very, very important to evaluate your material extensively and understand what's really happening inside the system. It's very, very important. So not only kinetics, also the mechanistic approach also has to be extensively studied with respect to using new ways of analyzing the materials, using new characterizations, using new methods like DFT or let's say machine learning modeling or something, so on and so forth. There are so many things that can be included in your work that can improve, advance your work, making your material much smarter, and so on and so forth. So what we saw there is TRL 1, 2, 3, or 4. So did we stop there? Everybody stops just at doing OER and HER, which is not advisable. You have to now push much further and try to test a device. What you can do, take your catalyst and develop a MEA like this using an anion exchange membrane or a proton exchange membrane with respect to whatever application you're working on, and try to develop a device out of it and try to test it. I do understand that we might not have the required setups or so on and so forth. That's where the collaboration comes into play. Start collaborating with some national institutions and professors in national institutions first. Try to establish a good bond with them, send your materials to them, and try to evaluate it, making it a collaborative paper, so that your paper or your work doesn't stop at an exploratory research. It moves further in a device level, moving up in the scale in the TRL level, which is highly, highly important. So what did we do? We did the AEM testing, and we did for different electrolyte, different temperature and everything. And we did a long-term study of 700 hours, which is still not that long, but okay. 700 hours at 500 milliamps. This is also something I will urge in this work is most of the people working on water splitting just are reporting the papers with respect to 10 milliamps long term or 100 milliamps long term, which is completely wrong. You have to move further, because think in such a way that if you are doing research with respect to industrial application, you want your material to be pushed further for industrial application. Do they work in industry with respect to 10 milliamps or 100 milliamps? No. They have high current densities, 1 ampere, 1.5 ampere, 2 ampere. At least go up the ladder, go to that level. And doing just for 12 hours or 24 hours in your device or in your overall water splitting is not that great. You have to push much further in doing a week, or you have to push your material. That's when you will understand what's happening to your material really. Because if you do a 10 milliamps or something, it's not really pushing your material. You're not really understanding anything in your material, where you're not asking the proper questions. You're just asking simple questions or making it easy so that the work is getting over, not your work is being pushed much further into advancement. This is something we have to really think about in doing devices. So this is very, very, very important. And I strongly urge that please push your material. See, it need not be electrolyzer. I'm speaking with respect to any application you're working on. The crystals have their own applications. Every nanomaterial has its own application. Your lab has different application perspectives you're working on. Don't stop with just testing the materials. Push further. Evaluate options with respect to making devices. Get tie-ups with industries. There are TBIs in your institutions, or if there is no TBI, no problem. Through your research consultancy program or through your dean of research or somebody, you can try to reach out for startup companies or something. Try to blend with them. Try to send your materials and work with them. These things can be done so that you can improve the way that you do research in any field that you're doing, not only electrolysis, in any field that you're doing, which is very important. Now, moving into ZAB, I'm just going to do it in 2 minutes. So we evaluated the ZAB. So we did the ORR studies with respect to using the RRDE apparatus, RDE and RRDE, rotating disc electrode based ring and rotating disc electrode, the setup. And we evaluated the material. Again, to be frank, it was not that great. It is not in the level of platinum and carbon or so, but still the material was able to work in that system. That what is very important. And our main approach is, I just want to evaluate my iron doped nickel orthoborate when compared to a fluorine included nickel orthoborate system. Is the fluorine bringing about a change in the activity? Yes, it's bringing about the change in activity, which you can see over here with respect to the TAFL values that we got, whereas the number of electron transfer is still very good. It has to be 4, and it was perfect over here. And we also extensively tested the material in methanol poisoning, long-term stability, RRD-based testing, H2O2 yield, and everything. And we found out that fluorine is really supporting and enabling the system to work much better. So you can ask me a simple question on, even though that you're not getting a good value, why to even report this? That's where we make the mistake. We just report the data only if we get very good values. That's not research. In research, what you can show here, it urges a research. For example, you can get an idea thinking that, oh, fine, if I bring in fluorine, it's altering such nature, which can be used in something that I'm doing, which can be used in a different application. This is what you have to give information on. When you bring in a fluorine, what really happens with respect to structure, with respect to morphology, with respect to internal nature, the chemical bonding nature, with respect to the output that you got. That is what you have to discuss much further. That makes your research much more advanced. That's what we have seen over here. And we didn't stop there. As I said, we pushed even further. We want to do a device. So what we did is we did the liquid type ZAB, and it had a very good output. Again, it's not a benchmarking level, but it was able to withstand a good nature. But the main nature is fluorine enabling it to work much better. So that is proved over here, that the fluorine is making it work much better, which is proved over here when we did the long-term studies, where the normal NFB electrocatalyst, what happened is after, let's say 40 hours, it started degrading slowly. And after around 115 hours, it completely degraded. It was destroyed completely. Whereas the fluorine-based structure was keeping on charging and discharge. Okay, there is loss, but it was stable and it was producing energy. And you can see over here that the galvanized discharge was much far better just when we brought in fluorine. So this work proves or explains to you that you need not do extensive based works or something. Even altering one single atom, you can bring about huge amount of data and huge amount of studies and scientific discussions that is needed, because that is very important. Just simply doing so many things is not necessary. You need to understand and evaluate very minor things when you're trying to do an exploratory research. And with that, you push further and make devices and so on and so forth, trying to get a much better output for your entire team, for your paper, for your students. Keep pushing your students so that they don't stick to the TRL 1 to 3. They move further, making devices. And also in TRL 1 to 3, they have to ask the proper questions. Why, what, and how. This has to be asked. So again, as I stated over there, we still didn't stop there. We went on to evaluate a zinc air battery cell, a quasi cell. We made a PVA gel out of the electrolyte and the PVA, and we made a small battery like cells, and we tested them. Again, the output is not that great, but still it was able to act and it was able to work in such nature also, proving that fluorine is enabling this material to be developed into a trifunctional catalyst. Still, there are flaws. Every work has its own flaws. There are flaws that are to be tested and to be corrected, but this gives out some of the best options on giving an understanding to a researcher that you ask the right questions and you just do a basic level research of just adding one single atom into my system brings about very good amount of scientific discussion and also understanding in various different applications. That's what I want to urge today, because to wrap up, I'm sorry I took too much time today. I hope I'll finish in like 5 minutes. I want to conclude this talk. I know I didn't go with respect to your conventional way of FDP, how it goes about, because I want to share and I want to convey this message properly in this development program, because it's a faculty development program where I need to convey something that might be helpful for you to develop your own research and to push your students much further. Please stop doing the first level research of just sticking on to TRL 1 to 3. Push much further. I do understand there are so many hurdles with respect to carrying out such research in our level, in terms of our colleges and stuff, but still nothing is going to stop you. All you have to do is work out plans so that you can bring about such output. Directly doing collaborations with international companies and international institutions is good, but not that advisable, because you need to have your own nature on understanding how a collaborative research works, so that you start with collaborating with national institutions, national labs, and so on and so forth, where there is the required equipments for your research. Try to do collaborative research so that you can push your research much further. Even for characterizations, you can do, for example, the XAS analysis is present in IIT Indore, which you can get used to, which is much cheaper. If back in here in Korea, it's very, very costly. One study is closer to, let's say, 60,000 rupees or something, whereas back in India, doing that XAS study, which not most of the people are using, costs around altogether 5 or 6,000 rupees. So such new characterizations can be brought into your application, whatever it may be. It need not be only water splitting. It can be any application that you want to work upon. Please devise a strategy. Start asking the right questions so that you can advance your work on very smarter materials, on very different applications. Don't stop with just evaluating the material. Please move on to device-based applications. Then slowly start collaborating with industries. Try to understand their requirement. Start supporting them with respect to testing materials and developing materials for them, which is also a very good research. What happens and what it gives to you is they will help you in return, where they will evaluate your material in commercial conditions. Or when you have a good material, they will jointly develop it and apply for patent. You can do a technology transfer to the industry where it is very good for your institution, for your lab, and for yourself. which is very, very important, which the researchers are not progressing into. The main important factor that you have to do industrial collaboration also. Try to work upon what is needed. It can be any application, as I said. It can be your application with a supercapacitor or crystal development or batteries, sensors, gas sensors, biosensors, anything. You have to have good collaborations, then slowly progress into international collaborations, tie-ups with different good labs, and trying to do visits over there, or trying to have student exchange programs. In such a way, develop much advanced in your research, trying to get much more advanced papers and advanced projects and so on. So I suggest start using much better characterizations. As I said, don't stick on to the basic level characterizations. Move much further. Start any applications, as I'm saying. You move on to in situ and operando studies with respect to different characterization I've stated over here, which will give a very good boost and very good data with respect to understanding the material or the device also, because in situ and operando studies can be done for the devices also. And as I kept on mentioning, have collaborations with the industries, institutions. Try to achieve much higher standard of papers, push much further in your own field, and please also try to come into this field of hydrogen generation, which is a very good field. The reason is this program is, as I said before, and I think others would have mentioned it also, government is pushing a lot of funding into hydrogen evolution, where please further move into it and try to write projects and try to acquire more funding so that you can do much more better and advanced researches. And as I said, this is just something that we do over here. This is basically the AMWE, PMWE, supercapacitors, batteries, zinc batteries, the liquid zinc batteries, quasi zinc batteries. And see, again, let's say you don't have a coin cell setup in your lab, so that you can say that, okay, John, I can't do coin cell based supercapacitors, which everybody is doing, because I don't have the required equipments to prepare it. You can make a pouch cell supercapacitor. It looks sophisticated, but it's very, very easy to prepare. Trust me, it's very, very easy to prepare when compared to a coin cell supercapacitor. Why not try it? It pushes your paper much further into the TRL levels and also in the impact factor level. And you can publish papers much more in higher Q1 journals, like the top 10% or top 5% journals, when you have such applications in your paper. So these are very important things that you need to do. The AMWs and PMWs might be costly in India. If you have projects, you can purchase and do it, or try making collaborations with companies or institutions and try to do it so that you can push much further. I hope this discussion has given you a clear picture, not only on the hydrogen-based hydrogen production based on electrolyzer, and also how to work on the topics. The main thing that I wanted to convey in this talk is on how to approach your research and how to make it better, because it's a development program, so that you can also advance your research, not just doing basic level research. Your research can be pushed further in a much advanced manner, and you can publish much advanced papers, get good projects, and have good patents and technology transfers and collaborations and industrial consultancy programs and so on and so forth, and international collaborations. And so that your lab, your institution, and yourself will be much far better. And that's what I hope this FDP trains you to do in this next few days also that you have. I hope it is helpful. This is a basic information about my research group, my boss and the students who are currently present, and also my personal information, that if you need some assistance or ideas or with respect to any doubts or something, you can feel free to contact me through email. Let's work out, and hopefully I can assist you with respect to your doubts or your problems with respect to achieving much better application or research in your own fields. It need be, because I'm not only doing research in electrolyzers, I'm doing work on electrolyzers, supercapacitor batteries, and so on and so forth. A lot of fields with respect to gas sensors, biosensors, and so on. But you should also evaluate different options in your labs, and so that it's much more versatile when you have different students in different applications, and also it enriches your entire portfolio. So with that, I will close my discussion. I am sorry for taking too much time. Thank you so much.
Thank you very much, sir, for your insightful and engaging session. We truly appreciate the time and effort you have taken to be with us today. Now, dear participants, the floor is open now for interaction. You are most welcome to ask your questions, to share your thoughts with our resource person. Please.
Thank you.
Yeah, good evening, Professor John.
Yes, sir.
Yeah, this is very nice work what you presented and very much close to my research field.
Okay.
So, yeah, thank you once again for your eye-opening session as well as your encouragement also. Basically, I
Yes, sir.
never thought after TRL what you told that after 3 we can
Yeah.
think and we can do. So now actually I get encouragement and I can do something.
True.
So it's fine. Very good. Thank you very much for that. But one
Okay.
thing, just I have just simple query that
Yeah.
in most of many papers I saw that
Mhm.
ECSA calculation, that surface area. So
Yeah.
is it really useful for characterization or for published paper? ECSA.
Okay. I will keep it in a simple manner for you. What you're working is what system? It's an electrochemical system, am I right? So in an
Yes.
electrochemical system, it's very important that you need to understand what's the surface area that you have, because you need to understand with respect to how many active sites are present, which has been actively working, and the data that you're getting. Am I right? Right now, ECSA is very important because a lot of the reviewers are asking you to present your LSV data based on ECSA, because
Yes.
the ECSA will change with respect to different coatings. I hope you understand that. Am I right? For the
Yes.
same
Yes.
material, for different coatings, the ECSA will change, which means that when you plot the data with respect to a normal LSV, when you do the current density, you do with respect to the area, 1 centimeter square or 2.5 centimeter square, with respect to whatever area that you have. Am I right? But that
Yes.
doesn't clearly imply on what is the real active area that is really acting on your output. So what right now they are doing is they are using the ECSA area and they are plotting the LSVs, which gives a clear picture on is it really the best material, because surface area also matters. There are some people who might debate saying that why not BET? They say why not BET? I'm asking a question like why BET? BET is basically where you do absorption desorption studies based on gas in a powder state. Does it directly imply on what is present in an electrochemical system for the coating that you have done, where there is binder and so on and so forth, you have the solvent and so on, where it's been completely. So you also know that you have an activation process that you do in the beginning so that you activate the material properly before starting your studies. So everything implies that ECSA is a very important study, and I will urge you so that in your papers, please use ECSA to plot LSV. You do the conventional LSV, no problem. That you use the current density based on your geometrical area, and you present the data. But also in your supplementary, you plot an LSV with respect to OE or H or anything with respect to ECSA.
Okay.
And prove that with respect to the active sites, this is the reaction, this is the output that I'm getting, confirming that this is the best material. So I will say that ECSA is a very, very important parameter that you have to have, not only in water splitting, in all electrochemical based application. It's not only for water splitting.
Yeah, actually, I asked this question because I published one paper in advanced material. So
Okay.
actually, we did not provide that ECSA calculation. So
Yeah.
reviewer actually asked. So we
Yeah.
had one argue.
Yeah.
And we can convince that reviewer
Yeah.
that ECSA is not that much useful, because
Yeah.
just what was our reason behind that, since our material is showing very good activity, that
Okay.
for each year actually that was published. So since it is showing already good activity, then what is the necessity to show ECSA value, ECSA surface area?
I
So
understand.
at last I convinced, and that got accepted and published. Just
Well, I
by the way,
understand.
one thing just my curiosity, that this very excellent work, means I really appreciate. And
Okay.
where you publish this? Where you publish this paper?
It's currently in under review in Joule.
Okay, okay, okay,
So
very good.
we are yet to get it. The reason I presented this one is because I can give much more detailed discussion on why such a research has to be carried out. Because we don't usually present what we are currently being it's under review, because we keep it to ourselves. But I wanted to explain this because I thought this might give a clear picture on don't do too much. Just work on what we have, and with that we can have a better output. Because you see, high impact papers, they don't do extensive decoration or extensive alteration or something. They take a smaller concept, they try to understand what's really happening inside, they try to understand why is it happening, and so on and so forth. They give a clear picture. That's why you go and read those papers to understand something, right? So why don't I do it? Why don't we do it? That's very important. That's what I'm trying to say, because our community has to work towards it, because that, I feel like that's lacking currently, and this FDP is for that, for advancement in research. So I know my talk might not be conventional, but I just wanted to convey these factors to the professors and the researchers over here.
Actually, your work, what you presented, means there is nothing left. It's like the perfectly explained, and every characterization as well as explanation you have done perfectly. Hope it will be accepted, and wish you good luck for your paper.
Thank you so much. I might contradict in that because I still feel there is a lot of works to be done. But anyway, thank you so much.
Yeah. Thank you.
Any more questions?
Thank you, participants, for your active involvement, and a special thanks to our resource person for patiently clarifying all the doubts. Now the feedback form will be link has been will be shared to in the chat box. I kindly request all the participants to fill it out without fail, as your feedback is very valuable to us. And on behalf of the organizing committee, I sincerely thank our respected management, principal, heads of departments, our resource person, Mr. John D. Rodney, and all the enthusiastic participants for making this session meaningful. Your support and participation keep this FTP successful.
Thank you, Professor. So I can leave, right? Is there anything else? Like any other questions or?
Yes, you can leave now.
Okay, thank you so much.
So participants, please fill up your feedback link form, and it will be available only for 5 minutes. So make it fast.